Light does not move. That sounds absurd. Every fiber of common sense tells you that light travels, that it crosses space, that it takes time to get from here to there. You flip a switch and the room lights up. The sun rises and photons stream across 93 million miles of empty space to warm your face. Of course, light moves, except it doesn't, not from its own perspective. From the reference frame of a photon, the journey from the surface of a star 10 billion light-years away to the back of your eye happens in exactly 0 seconds. No time passes, no distance is crossed. The photon is emitted and absorbed in the same instant, and everything in between, the entire observable universe, the birth and death of galaxies, the expansion of space-time itself, collapses to nothing. This is not a thought experiment. This is what the mathematics of relativity actually says happens at 299,792,458 meters per second, and for more than a century, physicists have known this number exists. They've measured it, they've confirmed it. They've watched particles in the Large Hadron Collider accelerate to 99.999991% of light speed and then slam into an invisible wall they can never cross. But knowing the limit exists is not the same as understanding why. Why this number? Why this speed? Why does the universe have a maximum at all? Richard Feynman found the answer buried in the quantum mechanics of light itself, and what he discovered changes everything. Because the speed of light is not a speed limit, it is not a barrier, it is the rate at which reality itself unfolds, it is the clock speed of existence. And once you see what that actually means, you cannot unsee it. This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. For thousands of years, light was simply the thing that happened when the sun came up. Nobody questioned how fast it moved, because the question itself seemed absurd. Light was just there, instantaneous, part of the furniture of the universe. You opened your eyes and you saw. The gap between opening and seeing was nothing, zero. The idea that light might take time to travel from an object to your eye was not even on the table for serious discussion. Philosophers debated the nature of vision, whether light entered the eye or whether the eye sent out rays to touch objects, but the speed of the process was assumed to be infinite. Light moved, if you could even call it movement, the way thoughts move, instantly. Galileo Galilei did not believe that. In 1638, Galileo was 74 years old, blind, and under house arrest. The Roman Inquisition had condemned him 7 years earlier for promoting the Copernican model of the solar system, the one where Earth moves around the sun instead of sitting fixed at the center of creation. He was forbidden from teaching, forbidden from publishing, forbidden from leaving his villa in Arcetri. So he did what any reasonable scientist under those conditions would do. He kept working. And one of the questions gnawing at him was whether light traveled instantaneously, or whether it simply moved so fast that no one had ever been able to measure the delay. He designed an experiment. Simple in concept, nearly impossible in execution. Take 2 observers, station them on hilltops a known distance apart, give each of them a lantern with a shutter they could open and close. Observer A would uncover his lantern. Observer B, standing on the distant hill, would watch for the flash. The moment B saw the light, he would uncover his own lantern. Observer A would then measure the time between uncovering his lantern and seeing B's response. Half of that time would be the delay caused by light traveling from A to B. The other half would be the delay of light traveling back from B to A. Subtract the time it takes a human to react, and you should be left with the time light spent in transit. Galileo tried it. He stationed an assistant roughly 1 to 3 miles away, depending on which historical account you trust. Both men held lanterns. Galileo uncovered his. The assistant uncovered his the moment he saw Galileo's light. Galileo measured the round trip. It did not work at all. The problem was not the concept. The concept was sound. The problem was scale. Light moves at 186,282 miles per second. Over a distance of 2 miles, light takes about 1,073 seconds to make the trip. The round trip, there and back, would take roughly 2,146 seconds. Human reaction time, the time it takes your brain to register a stimulus and your hand to respond, sits around 2 seconds. That is roughly 10,000 times longer than the signal Galileo was trying to detect. He was trying to time a bullet with a sundial. What Galileo measured was not the speed of light. It was the speed of his assistant's nervous system. And the result told him nothing except that if light did have a finite speed, it was far too fast for lanterns on hilltops to catch. He wrote up his findings in a book called Discourses and Mathematical Demonstrations Relating to Two New Sciences, published in 1638, despite the Inquisition's restrictions. In it, he described the experiment and admitted defeat. Light, he concluded, either traveled instantaneously or it traveled so extraordinarily fast that the delay could not be detected by available methods. He could not tell which. That was the state of the art for nearly 4 decades. The fastest thing in the universe, and humanity had no way to measure it, no way to even prove it had a speed. Then in 1676, a Danish astronomer named Olaus Rømer was sitting in Paris, watching Jupiter. Rømer was not trying to measure the speed of light. He was trying to solve a navigation problem. In the 17th century, figuring out your longitude at sea was one of the hardest unsolved problems in the world. You could measure latitude easily enough by looking at the sun or the stars, but longitude required accurate timekeeping, and mechanical clocks were not yet reliable enough to survive months at sea. One proposed solution was to use the heavens as a clock. Jupiter's moons, discovered by Galileo in 1610, orbited the planet on predictable schedules. Io, the innermost of the 4 large moons, passed into Jupiter's shadow and disappeared from view every 5 hours like clockwork. If you could publish accurate tables predicting when those eclipses would happen, sailors anywhere in the world could observe an eclipse, compare the time to the predicted time, and calculate how far east or west they were from the reference point. The Paris Observatory, where Rømer worked, was in charge of making those tables, and the tables were not working. The eclipses kept happening at the wrong times. When Earth was on the same side of the Sun as Jupiter, Io's eclipses occurred almost exactly on schedule. But as Earth moved in its orbit, gradually increasing the distance between itself and Jupiter, the eclipses started arriving late, not by seconds, by minutes. By the time Earth was on the opposite side of the Sun from Jupiter, roughly 6 months later, Io's eclipses were delayed by about 6 minutes compared to the prediction. Then, as Earth swung back around and the distance to Jupiter decreased, the eclipses gradually caught back up. 6 months later, they were on time again. Other astronomers noticed the discrepancy and assumed the tables were wrong. Maybe Io's orbit was not as regular as everyone thought. Maybe Jupiter's gravity was doing something weird. Maybe there was an error in the observations. Romer looked at the pattern and saw something else. The delays were not random. They correlated perfectly with Earth's position in its orbit. The further Earth was from Jupiter, the later the eclipses appeared. The closer Earth was, the more punctual they became. His explanation was simple and radical. Light was not instantaneous. It took time to cross space. When Earth was far from Jupiter, the light carrying the image of Io's eclipse had to travel a longer distance to reach an observer's telescope. That extra distance added a delay. When Earth was close to Jupiter, the distance was shorter and the delay was smaller. The 16.6-minute variation was the time it took light to cross the diameter of Earth's orbit. Nobody had ever considered that possibility. Light was supposed to be instant. That was the default assumption baked into every astronomical observation ever made. But Romer's explanation fit the data so cleanly that it was hard to dismiss. If light took time to travel, then every observation of a distant object was not showing you the object as it was now, but as it had been some time ago when the light left. The further away the object, the older the image. Romer presented his findings to the French Academy of Sciences in 1676. He did not calculate an exact speed for light because the diameter of Earth's orbit was not known precisely at the time. But other scientists, using the best available estimates of that diameter, worked backward from his observations and arrived at a figure of roughly 214,000 kilometers per second. The modern value, measured to absurd precision using lasers and atomic clocks, is 299,792,458 kilometers per second. Romer's estimate, extracted from the timing of a moon eclipse observed through a 17th century telescope, was off by about 29%. That is astonishingly close given the tools he was working with. He had no laser interferometers, no synchronized clocks, no computers, no way to measure distances in space except by indirect calculation. He watched Jupiter's moons, noticed a pattern, and deduced that light had a speed. That alone was enough to overturn centuries of assumption. Not everyone believed him. Christian Huygens, one of the most respected physicists of the era, accepted Romer's conclusion and used it to estimate the speed of light in his own work. But others were skeptical. The French astronomer Jean-Dominique Cassini, Romer's own supervisor at the Paris Observatory, rejected the idea. He argued that the variations in Io's eclipses were caused by irregularities in the moon's orbit, not by delays in light propagation. The debate simmered for years. Gradually, as more observations accumulated and as other phenomena, like the aberration of starlight discovered by James Bradley in 1728, provided independent evidence that light had finite speed, the skeptics gave up. By the mid-18th century, it was settled. Light moved. It moved fast, but it moved, and that meant the universe was older than any light reaching your eye. Still, 214,000 kilometers per second was just an estimate. A good estimate, but not a measurement. For that, you needed to measure light speed directly on Earth, under controlled conditions, without relying on the orbits of distant planets. That turned out to be extraordinarily difficult. The first person to pull it off was Hippolyte Fizeau, a French physicist working in 1849. His method was ingenious. He built a rotating toothed wheel with 720 notches cut into its edge. On one side of the wheel, he placed a light source. On the other side, more than 8 kilometers away, he placed a mirror. Light from the source would pass through one of the notches in the wheel, travel to the mirror, reflect back, and return through the same notch, assuming the wheel had not moved. But if the wheel was spinning fast enough, by the time the light returned, the wheel would have rotated just enough that a tooth would block the returning beam instead of a notch. By measuring the speed of the wheel at the exact moment the returning light was blocked, Fizeau could calculate how long the light had spent in transit. His result was approximately 315,000 kilometers per second. Not perfect, but close enough to confirm that Romer was in the right ballpark. 13 years later, in 1862, Léon Foucault improved the technique using a rotating mirror instead of a toothed wheel. The mirror method was more precise because it eliminated the mechanical irregularities inherent in cutting evenly spaced teeth. Foucault's result was 298,000 kilometers per second, within 0.5% of the modern value. He also discovered something else. Light moved slightly slower in water than in air, which had profound implications for understanding the nature of light itself. If light was a wave, as many scientists suspected, then it must be a wave traveling through some medium. And that medium, whatever it was, had to behave differently depending on whether it was empty space, air, or water. By the late 19th century, the speed of light was no longer a mystery. It was a number. A very precise number that every competent physicist could measure with the right equipment. But the precision created a new problem. Because once you knew exactly how fast light moved, you had to explain why it moved that fast. Why 299,792 kilometers per second and not some other value? Why was that number the same in every experiment, no matter who performed it, no matter when, no matter where? Galileo's lantern experiment failed because he was trying to measure something too fast for the tools he had, but the failure was not pointless. It established that light, if it had a speed at all, was faster than anything else humans had experience with. Faster than sound, faster than a cannonball, faster than a sprinting horse or a diving falcon. The experiment set a lower bound. Light was at least fast enough to be unmeasurable by human reaction time over short distances. That was progress. Negative results are still results. Romer succeeded because he did not try to measure light directly. He measured the consequences of light having a finite speed. He looked at the shadows cast by a moon 500 million kilometers away and noticed that the shadows were always a little bit late when Earth was far from Jupiter. That delay was the fingerprint of a traveling signal. He did not need to catch the light in motion. He just needed to notice that motion had occurred. Fizeau and Foucault succeeded because they built machines fast enough to interact with light on its own timescale. A rotating mirror or a spinning toothed wheel does not have human reaction time. It moves mechanically, predictably, at speeds that can be controlled and measured. By matching the speed of their apparatus to the speed of the thing they were trying to measure, they closed the gap that had defeated Galileo. Each step forward depended on the step before it. Galileo proved the question was worth asking. Romer proved the answer was finite. Fizeau and Foucault proved the answer could be measured on Earth without waiting for planetary alignments. And by the time the 20th century arrived, the speed of light was no longer a curiosity. It was infrastructure. It was a constant that showed up in equations describing electricity, magnetism, and the behavior of matter at the smallest scales. But knowing the number is not the same as understanding what the number means. Why does light move at that speed? Why does nothing move faster? What is light actually doing when it crosses space at 299,792,458 meters per second? Those questions could not be answered by a rotating mirror or a toothed wheel. They required a different kind of experiment. They required someone willing to rethink the nature of space, time, and motion itself. That someone was already alive in 1862 when Foucault published his results. He was 3 years old, living in the German kingdom of Württemberg, and his name was Albert Einstein. Albert Einstein did not set out to destroy the universe. He was trying to fix a smaller problem, a much smaller problem. The equations describing electricity and magnetism, worked out by James Clerk Maxwell in the 1860s, did not play nicely with the equations describing motion, worked out by Isaac Newton 2 centuries earlier. When you tried to apply both sets of rules to the same situation, something broke. And Einstein, who was 26 years old in 1905 and working as a patent clerk in Bern, Switzerland, because no university would hire him, decided that the thing breaking was not the equations, it was the assumptions underneath them. The problem was light. Maxwell's equations predicted that oscillating electric and magnetic fields could propagate through space as waves, and when you calculated the speed of those waves, you got a number, 299,792 kilometers per second. The same number Fazot and Foucault had measured in their labs. Maxwell had not set out to calculate the speed of light. He had set out to describe how electricity and magnetism worked. The fact that his equations spit out the exact speed of light as a natural consequence was one of those accidents that stops being an accident the moment you notice it. Light was an electromagnetic wave, that much was clear, but waves need something to wave in. Water waves move through water. Sound waves move through air. Earthquake waves move through rock. If light was a wave, what was doing the waving? The answer, according to every physicist in the 19th century, was the ether, an invisible, weightless, perfectly transparent substance that filled all of space, permeating everything, allowing light to propagate the way air allows sound to travel. The ether was not optional, it was required. Without it, Maxwell's equations described a wave with nothing to wave in, which made no sense. So the ether had to exist, even though no one had ever detected it, measured it, or explained what it was made of. The ether had a problem. If it existed, and if Earth was moving through it as the planet orbited the Sun, then the speed of light should depend on your direction of motion relative to the ether. Imagine you are standing in a river. Throw a ball upstream and it moves slower relative to the ground because it is fighting the current. Throw it downstream and it moves faster because the current carries it. Light moving through the ether should behave the same way. If Earth is moving through the ether at 30 kilometers per second as it orbits the Sun, then light traveling in the same direction as Earth's motion should appear to move faster than light traveling perpendicular to it. The difference would be tiny, but it should be there. In 1887, 2 American physicists named Albert Michelson and Edward Morley built an instrument sensitive enough to detect that difference. They called it an interferometer. The design was elegant. A single beam of light was split into 2 perpendicular beams using a half-silvered mirror. One beam traveled along a path parallel to Earth's motion through the ether. The other beam traveled perpendicular. Both beams bounced off mirrors at the ends of their paths and returned to the starting point, where they recombined. If one beam had traveled through the ether faster than the other, the 2 beams would be slightly out of phase when they met, and that phase difference would show up as a shift in the interference pattern, the alternating light and dark fringes created when the 2 beams overlapped. Michelson and Morley ran the experiment. They rotated the entire apparatus to change the orientation of the beams relative to Earth's motion. They repeated the test at different times of day, different times of year, trying every possible configuration to catch the ether wind. The interference pattern should have shifted. It did not. Not even a little. the two beams of light, one supposedly moving with the ether current and one supposedly moving across it, arrived back at the same time every single time. The speed of light was the same in both directions, exactly the same. That result made no sense. If the ether existed, the experiment should have detected it. The apparatus was sensitive enough, the logic was sound, but the data said the ether wind was not there. Some physicists suggested that maybe Earth was dragging the ether along with it, the way a moving ship drags a thin layer of water along its hull. That did not work either, because other experiments showed that light from distant stars was not dragged. Others proposed that objects moving through the ether contracted slightly in the direction of motion, just enough to compensate for the speed difference. That idea, developed independently by George Fitzgerald and Hendrik Lorentz, actually worked mathematically, but it felt like a patch, a fix designed specifically to explain one experiment without explaining why the universe would bother to arrange itself that way. Einstein looked at the Michelson-Morley result and arrived at a different conclusion. The ether did not exist. Light did not need a medium. It propagated through empty space on its own, and its speed was not relative to anything. It was absolute. The same for every observer, no matter how they were moving. That was the second postulate of what would later be called special relativity. The speed of light in vacuum is the same in all inertial reference frames, regardless of the motion of the source or the observer. The first postulate was older and less controversial. The laws of physics are the same in all inertial reference frames. An inertial reference frame is just a fancy term for any perspective that is not accelerating. If you are sitting still, you are in an inertial frame. If you are moving at constant velocity in a straight line, you are also in an inertial frame. The laws of physics do not care which of those situations you are in. A ball thrown inside a train moving at constant speed behaves exactly the same as a ball thrown inside a stationary room. Galileo had figured that much out in the 1630s. Einstein was not breaking new ground with the first postulate. He was just stating it clearly. The second postulate was the bomb. If the speed of light is the same for all observers, then something else has to give. And what gives is time and space, both of them, at the same time. Here is why. Imagine you are standing on a train platform. A train goes past you at half the speed of light. Inside the train, someone turns on a flashlight and points it forward, in the direction the train is moving. You, standing on the platform, measure the speed of the light coming out of that flashlight. What do you measure? According to everyday intuition, you should measure the speed of light plus the speed of the train. If the train is moving at half the speed of light, and the light inside the train is moving at the full speed of light relative to the train, then relative to you, the light should be moving at 1.5 times the speed of light. It does not. You measure the speed of light. Exactly the speed of light, the same speed the person on the train measures. The light does not care that the train is moving. It moves at the speed of light, full stop, the same for both of you. That is not possible unless time is running differently for you and the person on the train. If the person on the train is moving relative to you, their clock has to be ticking slower, not because their clock is broken, because time itself, the thing clocks measure, is passing more slowly for them than it is for you. This is called time dilation, and it is not a theory, it is a measured fact. Atomic clocks flown on airplanes tick slower than atomic clocks left on the ground. Particles called muons, created high in the atmosphere by cosmic rays, should decay long before they reach the surface if you calculate their lifetimes using their own internal clocks. But from Earth's perspective, they live longer because time is moving slower for them. They make it to the ground. We detect them. Time dilation is real. Length contracts too. If you are moving relative to an object, that object appears shorter in the direction of motion. Not because it is physically squished, because space itself is compressed along the direction of travel. A meter stick moving past you at near light speed is no longer a meter long from your perspective. It might be half a meter or a tenth of a meter. The closer it gets to the speed of light, the shorter it becomes. At exactly the speed of light, its length in the direction of motion would be zero. But nothing with mass ever gets there, so that case never happens. The contraction is not something the object feels. From the object's perspective, it is still a meter long. You are the one who is contracted. Both of you are right. Space and time are not absolute. They depend on who is measuring. Einstein worked all of this out using nothing but Maxwell's equations, basic algebra, and a willingness to take the constancy of the speed of light seriously. He did not have experimental data that directly confirmed time dilation or length contraction when he published his paper in 1905. He had the Michelson-Morley null result, which told him the speed of light was constant, and he had the logical consequences of that fact. He followed the math wherever it led, and it led to a universe where time and space were flexible, interwoven, and dependent on motion. He called the paper On the Electrodynamics of Moving Bodies, and he sent it to Annalender Physik, one of the leading physics journals in Europe. It was published in September 1905. It did not include the equation E equals mc squared. That came later in a follow-up paper published just a few months afterward. The mass-energy equivalence was not obvious from the original paper, but it was implied. If the speed of light is constant, and if energy and momentum have to be conserved in all reference frames, then mass and energy cannot be separate things. They have to be two forms of the same thing. Mass is concentrated energy. Energy is dispersed mass. The relationship between them is E equals mc squared. Energy equals mass times the speed of light squared. That squared term is what makes the equation powerful. The speed of light is a huge number. Squaring it makes it enormous. A tiny amount of mass corresponds to a staggering amount of energy. 1 kilogram of matter, if you could convert it entirely into energy, would release about 90 quadrillion joules. That is roughly the energy output of the largest nuclear weapon ever tested, the Soviet Tsar bomber, which weighed 27,000 kilograms and converted about half a gram of mass into explosive force. Half a gram. The rest of the bomb's mass stayed mass. But that half gram was enough to produce a fireball 5 miles wide and a mushroom cloud that rose 40 miles into the stratosphere. Einstein did not have nuclear bombs in mind when he derived the equation. He was not trying to build weapons or power plants. He was trying to understand why the laws of electromagnetism and the laws of motion seemed to contradict each other. The equation fell out of the math as a consequence of the speed of light being constant. If c is the same for everyone, and if energy and momentum have to work out consistently in all frames of reference, then mass has to be a form of energy. There is no other way to make the numbers add up. The equation had skeptics. Some physicists argued that Einstein had only shown that energy added to an object increased its mass, not that all mass was energy. That debate simmered for a couple of years until Einstein refined the argument in 1907 and showed that yes, all inertial mass was equivalent to energy. Even the so-called rest mass, the mass an object has when it is sitting still, that mass is energy too. Just energy that is not going anywhere. Wolfgang Rindler, a physicist who spent decades studying relativity, once commented that extending the equivalence to all mass, not just the mass added by motion, required an act of aesthetic faith, very characteristic of Einstein. The equation worked, the experiments confirmed it. But the leap from some mass is energy to all mass is energy was bold in a way that only someone willing to rebuild the universe from scratch would attempt. The most immediate consequence of special relativity, the one that turned the speed of light into a universal speed limit, was not about energy or bombs, it was about acceleration. If you want to make something go faster, you have to add energy. The faster it is already going, the more energy you need to add to make it go even faster. As an object's speed approaches the speed of light, the amount of energy required to accelerate it further increases without bound. At 90% of light speed, you need a lot of energy to go faster. At 99%, you need vastly more. At 99.9%, the energy requirement becomes absurd. At exactly the speed of light, the energy required would be infinite, and since infinite energy is not available, nothing with mass ever reaches light speed. The speed of light is not a barrier you slam into. It is an asymptote you approach forever without ever arriving. Light itself has no trouble moving at the speed of light because light has no mass. Photons, the particles that make up light, are massless. That does not mean they have no energy. They have plenty of energy, but their energy comes from their motion, not from their mass, because they do not have mass to begin with. A photon at rest is a contradiction in terms. There is no such thing. Photons are always moving at the speed of light. They are born moving at that speed. They spend their entire existence moving at that speed, and they cease to exist the moment they are absorbed by something. They do not accelerate. They do not slow down. They move at c, always, in every reference frame, because that is the only speed they are allowed to have. Einstein's 1905 paper did not prove that the speed of light was constant. It assumed it, and then asked what the universe would have to look like if that assumption were true. The answer was that space and time could not be what everyone thought they were. They had to be flexible, observer-dependent, interconnected. That was the price of keeping the speed of light constant, and once you paid that price, everything else followed. Time dilation, length contraction, mass-energy equivalence, the cosmic speed limit, the unification of space and time into a single four-dimensional structure that Einstein and his former professor Hermann Minkowski called spacetime. All of it was sitting inside those two postulates, waiting to be unpacked. The physics community did not embrace special relativity immediately. The paper was strange. The conclusions were counterintuitive. Time running at different rates for different observers sounded like philosophy, not physics. But the math worked, and more importantly, the predictions worked. In 1909, experiments with fast-moving electrons confirmed that their behavior matched Einstein's equations, not Newton's. In 1932, particle accelerators began producing clear evidence of time dilation in unstable particles. By the mid-20th century, special relativity was no longer controversial. It was infrastructure. Engineers designing particle accelerators had to account for relativistic effects, or their machines would not work. GPS satellites have to correct for time dilation, or the system would accumulate errors of several kilometers per day. The effects are small at everyday speeds, but they are real and they add up. Einstein did not invent the idea that space and time were related. Lorentz and Fitzgerald had already developed equations that described length contraction and time dilation, but they thought those effects were real physical changes caused by motion through the ether. Objects really contracted, clocks really slowed down, because the ether was doing something to them. Einstein's insight was that there was no ether. The effects were not caused by motion through a medium. They were caused by the structure of spacetime itself. Space and time were not a stage on which events happened. They were part of the event. Measuring space meant measuring time. Measuring time meant measuring space. The two were inseparable, and the thing connecting them was the speed of light. The speed of light is not fast, because light is special. Light moves at the speed of light because that speed is built into the geometry of spacetime. It is the conversion factor between space and time. 1 second of time corresponds to 299,792,458 meters of space. That is not arbitrary. That is the exchange rate the universe uses when translating between the two. And because that exchange rate is fixed, the speed of light is fixed. It is the same in every direction, at every location, for every observer, because it is not really the speed of light, it is the speed of causality. It is the fastest speed at which cause can propagate to effect. It is the maximum rate at which information can move from one point in spacetime to another. Light happens to travel at that speed because photons have no mass, so there is nothing slowing them down. But the speed itself is not about photons, it is about the universe. By the time Einstein published his paper, Fizeau's rotating mirror and Foucault's improved measurements had already pinned down the speed of light to within a fraction of a percent. What Einstein did was explain why that number mattered, why it was not just a speed, but the speed, the upper limit on velocity, the fixed constant that refused to change no matter how you moved or what you measured. The thing that forced space to contract and time to dilate so that every observer, moving or stationary, would measure the same value. The universe does not care how uncomfortable that makes you. It does not care that time dilation sounds impossible or that mass-energy equivalence seems absurd. The rules are the rules, and the speed of light is the thread holding those rules together. Pull on it, and the entire structure shifts. Einstein pulled on it and discovered that space and time were not two separate things. They were coordinates in a single unified geometry, and the speed of light was the constant that locked that geometry in place. There were still questions, big ones. Special relativity applied to objects moving at constant speeds, but it said nothing about acceleration or gravity. Einstein would spend the next decade working on that problem, and the result would be general relativity, an even stranger theory that described gravity not as a force, but as the curvature of spacetime itself. But general relativity was built on the foundation of special relativity. Without the constancy of the speed of light, none of it would have worked. The speed of light was the keystone. Everything else was commentary. And if the speed of light truly was the universe's absolute speed limit, if nothing could ever move faster, then what happened when you tried? What would happen if you built a machine capable of accelerating particles to speeds so close to light speed that the difference was measured in parts per million? What would you see? Would the particles hit a wall? Would they simply refuse to go faster, no matter how much energy you fed them? Or would something stranger happen? Something nobody in 1905 could have predicted, because the tools to test it did not exist yet. By the 21st century, those tools existed. They sat beneath the border between France and Switzerland, in a tunnel 27 kilometers around, pushing protons to within a hairbreadth of the speed of light and smashing them together to see what would happen. The universe had rules. Humans had built a machine to test them. And if the speed of light truly was the universe's absolute speed limit, if nothing could ever move faster, then what happened when you tried? What would happen if you built a machine capable of accelerating particles to speeds so close to light speed that the difference was measured in parts per million? What would you see? Would the particles hit a wall? Would they simply refuse to go faster, no matter how much energy you fed them? Or would something stranger happen? Something nobody in 1905 could have predicted because the tools to test it did not exist yet. By the 21st century, those tools existed. They sat beneath the border between France and Switzerland, in a tunnel 27 kilometers around, pushing protons to within a hairbreadth of the speed of light and smashing them together to see what would happen. The Large Hadron Collider is not subtle. It is the largest machine humanity has ever built, a ring of superconducting magnets stretching 659 kilometers in circumference, buried 100 meters underground near Geneva. The tunnel itself was dug in the 1980s for an earlier, less powerful accelerator. When that machine was decommissioned, physicists looked at the empty tunnel and thought, what if we built something bigger? What if we pushed particles harder than they had ever been pushed before? What if we accelerated protons to speeds so close to the speed of light that the gap between their velocity and the cosmic speed limit was narrower than the width of a human hair compared to the distance across a continent? They built it. It cost roughly 10 billion Swiss francs. It took thousands of scientists from over 100 countries more than a decade to design, construct, and bring online. On September 10, 2008, engineers fired the first beam of protons into the ring. The beam completed one full lap. Physicists cheered. 9 days later, a faulty electrical connection between two superconducting magnets caused a catastrophic failure. Liquid helium exploded into the tunnel. 53 magnets were damaged. The machine was shut down for more than a year while repairs were made. When it finally came back online in November 2009, it worked. And it has been working, with intermittent upgrades and maintenance shutdowns ever since. The purpose of the LHC is simple in concept. Take two beams of protons, accelerate them to nearly the speed of light in opposite directions, and smash them into each other. The collisions recreate conditions that existed in the first trillionth of a second after the Big Bang, when the universe was so hot and so dense that matter as we know it had not yet formed. By studying what comes out of those collisions, physicists can test predictions about the fundamental particles and forces that make up reality. They can search for new particles. They can measure the properties of known particles with absurd precision. They can probe the edge of the Standard Model, the reigning theory of particle physics, looking for cracks. And they can test Einstein's equations in ways that would have been impossible in 1905. Because the LHC does not just accelerate particles, it accelerates them to 9,999,991% of the speed of light. That number is not an approximation. That is the actual measured speed of protons circulating in the LHC at maximum energy. The machine accelerates protons to 7,000 giga-electron volts, written as 7 TeV in the shorthand physicists use. When two beams collide head-on, the total collision energy is 14 TeV. That is the highest energy ever achieved in a particle collider. The previous record holder, the Tevatron at Fermilab in Illinois, topped out at 2 TeV. The LHC is 7 times more powerful, and that factor of 7 makes all the difference when you are trying to explore physics at the smallest possible scales. At 9,999,991% of the speed of light, a proton in the LHC is moving at roughly 299,792,457, 73 meters per second. The speed of light in vacuum is 299,792,458 meters per second. The difference is about 1/4 of a meter per second. A human can walk faster than that. A proton circling the LHC at top speed is lagging behind a photon by less than the pace of a leisurely stroll. And yet, that tiny gap, that last 0.9%, is unbridgeable. Not because the engineers ran out of money or because the magnets are not strong enough. It is unbridgeable because the universe says so. Here is what happens when you try to accelerate a particle closer to the speed of light. You add energy. The particle speeds up. You add more energy. The particle speeds up a little less. You keep adding energy, and the speed increases, gets smaller and smaller. At low speeds, adding energy gives you a proportional increase in velocity. Double the energy, double the speed. At high speeds, that relationship breaks down. By the time you are at 90% of light speed, doubling the energy does not double the speed. It barely budges it. At 99%, you can pour in 10 times as much energy and the speed increase is microscopic. At 9,999,991%, you are adding enormous amounts of energy, and the particle is moving faster by amounts so small that the difference is almost philosophical. This is not a failure of engineering. It is a consequence of special relativity. As a particle's speed approaches the speed of light, its energy does not just go into making it move faster. Most of the energy goes into increasing the particle's relativistic mass. From the perspective of a stationary observer, the particle gets heavier, not because it is gaining matter, because the energy you are pumping into it is manifesting as mass. E equals mc squared works both ways. Mass is energy, energy is mass. When you add kinetic energy to a particle moving at relativistic speeds, that energy shows up as an increase in the particle's inertia, the resistance it has to further acceleration. At 9,999,991% of light speed, a proton in the LHC has a relativistic mass roughly 7,460 times greater than its rest mass. Its rest mass, the mass it has when sitting still, is about 167 times 10 to the negative 27 kilograms. Multiply that by 7,460 and you get the effective mass the proton has while moving at full speed. That increased mass means it takes 7,460 times as much force to accelerate it further compared to accelerating a stationary proton by the same amount. And the closer you get to light speed, the worse the problem becomes. The relativistic mass increases without limit. At exactly the speed of light, the mass would be infinite. Accelerating an infinite mass requires infinite energy. Infinite energy does not exist, so the particle never gets there. The LHC accelerates protons using electromagnetic fields. The ring is lined with superconducting radio frequency cavities that generate oscillating electric fields. As a proton passes through a cavity, the field gives it a kick, adding energy. The proton moves a little faster. It continues around the ring and passes through the next cavity, which gives it another kick, then another, then another. Each kick adds energy. The proton accelerates. After enough kicks, the proton is moving at a significant fraction of the speed of light, but the kicks do not stop. The proton keeps circling the ring, passing through the cavities over and over, accumulating energy with each pass. It takes roughly 20 minutes for a proton to go from injection speed to maximum energy. During that time, the proton completes millions of laps. Each lap, it gets faster. Each lap, the amount of speed gained from the same energy input gets smaller. At maximum energy, a proton in the LHC circles the ring 11,245 times per second. That is 11,245 laps over 26, 659-kilometer track every second. The proton is covering more than 299,000 kilometers every second, which is almost exactly the speed of light. Almost. The ring is a circle, which means the proton is constantly turning. Turning requires acceleration. Even at constant speed, an object moving in a circle is accelerating because its direction is changing. That centripetal acceleration has to be provided by something, and in the LHC it is provided by 1,232 superconducting dipole magnets. Each magnet is about 15 meters long and generates a magnetic field of 3 Tesla, roughly 100,000 times stronger than Earth's magnetic field. The magnets bend the proton's path just enough to keep them circling the ring instead of flying off in a straight line. The magnets have to be superconducting because a normal electromagnet strong enough to bend the path of a 7 TeV proton would require so much electrical current that the heat generated would melt the wiring. Superconductors carry current with zero resistance, which means they generate no heat. But superconductors only work at extremely low temperatures. The LHC's magnets are cooled to 9 Kelvin, which is -271, 3 degrees Celsius, or -456, 34 degrees Fahrenheit. That is colder than outer space. The cooling system uses liquid helium, about 96 metric tons of it, circulating through the entire 27-kilometer ring. The LHC is the largest cryogenic system ever built. It has to be. Without those temperatures, the magnets do not work. Without the magnets, the protons fly into the walls. Without the protons, there are no collisions, and without collisions, there is no physics. Inside the ring, the environment is as close to a perfect vacuum as human technology can create. The pressure is about 10 to the -13 atmospheres. That is a quadrillion times less dense than the air you are breathing. If there were gas molecules floating around inside the beam pipe, the protons would collide with them instead of with each other, and the experiment would fail. So the interior of the LHC is emptier than the space between stars. There is nothing in that tunnel except protons moving at nearly the speed of light and the electromagnetic fields guiding them. When two proton beams collide, they do not hit like billiard balls. Protons are not solid objects. They are bundles of quarks held together by the strong nuclear force, and when two protons collide at 14 TeV, the quarks inside them interact directly. The collision does not just break the protons apart. It converts kinetic energy into new particles. Particles that did not exist a microsecond earlier suddenly pop into existence, created from the energy of the impact. Most of those particles are unstable and decay almost instantly into lighter particles, which decay into even lighter particles, until eventually you are left with stable things like electrons and photons that the detectors can measure. The LHC generates about 600 million proton-proton collisions every second when it is running at full intensity. Not every collision is interesting. Most are glancing blows that produce nothing unusual, but every so often a collision produces something rare, a Higgs boson, a top quark pair, a configuration of particles that has never been seen before. The detectors, enormous multi-story instruments built around the collision points, record what comes out. They contain roughly 150 million sensors. Every collision is photographed, measured, analyzed. The data pours out at a rate of about 15 petabytes per year. That is 15 million gigabytes. No human could sift through that much information manually. So the LHC uses automated systems to filter the data in real time, discarding the boring collisions and keeping the potentially interesting ones for closer study. Even with filtering, the amount of data generated by a single year of LHC operations is staggering. The machine consumes about 600 gigawatt-hours of electricity per year when it is running. That is enough to power a city of 100,000 people for the same period. The electricity goes into the magnets, the cooling system, the radio frequency cavities, the detectors, and the computing infrastructure needed to process the data. The LHC is not an efficient machine by everyday standards, but efficiency is not the point. The point is to push particles to the edge of what physics allows and see what happens. On December 15, 2009, the LHC reported its first physics results. The ALICE experiment recorded 284 collisions. That was enough to prove the detectors were working. On July 4, 2012, physicists at CERN announced that they had discovered the Higgs boson, a particle predicted by theory in the 1960s but never directly observed until the LHC found it. The Higgs boson is the particle associated with the Higgs field, the field that gives other particles their mass. Without the Higgs field, electrons and quarks would be massless, and atoms could not exist. Neither could you. The discovery confirmed a cornerstone of the Standard Model and earned Peter Higgs and Francois Englert the Nobel Prize in Physics in 2013. The Higgs boson has a mass of about 126 giga-electron volts. That is roughly 133 times heavier than a proton. It exists for about 10 to the negative 22nd seconds before decaying into lighter particles. You cannot see it, you cannot hold it. You can only infer its existence by analyzing the debris left behind when it decays. The LHC has produced millions of Higgs bosons since 2012, and physicists are still measuring its properties with ever-increasing precision, looking for deviations from the predictions. So far, the Higgs behaves exactly as the Standard Model says it should. No surprises, no cracks. As of February 2026, the LHC has discovered 79 new hadrons. Hadrons are particles made of quarks. Protons and neutrons are hadrons. So are pions and kaons, and a menagerie of heavier, more exotic particles that only exist for fractions of a second before decaying. Most of the new hadrons found at the LHC are not revolutionary. They are confirmations of what theory predicted should exist but had never been seen directly. Finding them is like filling in the periodic table. It does not change the framework, but it completes the picture. On September 18, 2024, the ATLAS experiment, one of the 4 main detectors at the LHC, observed quantum entanglement between quarks at the highest energy ever recorded. Entanglement is a quantum phenomenon where 2 particles become linked in such a way that measuring one instantly affects the other, even if they are separated by large distances. Einstein called it spooky action at a distance and was deeply uncomfortable with it. The observation at the LHC did not prove entanglement, that was settled decades ago. But it showed that entanglement persists even in the violent high-energy environment of a 14 TeV proton collision. The universe does not stop being quantum just because things are moving fast. The LHC has run in 3 phases so far, called Run 1, Run 2, and Run 3. Each run lasts several years and is followed by a shutdown period during which the machine is upgraded. Run 1 lasted from 2010 to 2013. Run 2 lasted from 2015 to 2018. Run 3 began in 2022 and is ongoing as of early 2025. Between runs, engineers install new magnets, improve the cooling systems, upgrade the detectors, and increase the beam intensity so that more collisions happen per second. Each upgrade pushes the LHC closer to its design limits. But even at those limits, the protons never get closer to light speed than 9,999,991%. That last sliver of velocity is permanently out of reach. Why is that gap unbridgeable? Because closing it would require infinite energy, not a large amount of energy, not an impractical amount, infinite, to accelerate a proton from 9,999,991% of light speed to 100% would require more energy than exists in the observable universe. Not because protons are heavy, because the equations of relativity say that the energy required to reach exactly the speed of light diverges to infinity as you approach it. The curve is asymptotic. You can get closer and closer, but the distance remaining never quite reaches zero, and the energy cost for each step forward grows without bound. This is not a technological limitation. It is a law of nature. The LHC is not failing to reach light speed. It is demonstrating with exquisite precision that Einstein was right. The speed of light is not just fast. It is the boundary of what is possible for anything with mass. Light itself moves at that speed because photons have no mass, so there is nothing holding them back. But protons have mass, electrons have mass, you have mass, and as long as mass exists, the speed of light remains untouchable. The LHC has confirmed this in the most direct way possible. Engineers have poured billions of dollars and decades of work into building a machine explicitly designed to accelerate particles as fast as physically possible. They have used the strongest magnets, the coldest temperatures, the most intense electromagnetic fields, and the most sophisticated control systems ever created. And the result is 9,999,991%. Not 100%, not 99,999,999%. The number does not keep growing, it stops, because the universe has rules, and one of those rules is that nothing with mass ever reaches the speed of light. That gap, that final 0.9%, is not empty space waiting to be crossed. It is a wall, not a physical wall, a mathematical one. A wall built into the structure of space-time itself. Every time the LHC adds more energy to a proton, the proton gets a tiny bit faster and a lot heavier. The speed approaches the limit, but it never crosses it. The energy keeps going in, but most of it is not going into motion anymore. It is going into mass. The proton becomes a tiny, impossibly dense packet of kinetic energy wrapped around a few quarks, moving at almost light speed, but never quite arriving. And the detectors measure all of this. They measure the energy, they measure the momentum, they measure the decay products. Every measurement confirms the equations. Every collision is a test of relativity, and relativity passes every time. The LHC is not just a particle collider. It is a proof of concept. It is a 27-kilometer ring of experimental evidence showing that the speed of light is exactly what Einstein said it was. A limit, not a suggestion, not a guideline, a hard boundary baked into the fabric of reality. If you could somehow add infinite energy, the equations say the particle would reach light speed, but you cannot add infinite energy. Infinite does not exist in the real world. The number of nines grows. The gap shrinks, but it never closes. That is what it means for light speed to be a limit. Not that it is hard to reach, that it is impossible to reach. The universe does not care how clever your engineering is. The rules do not bend. And those rules have consequences, because if nothing with mass can reach the speed of light, then time and space must behave in ways that enforce that limit. They do. And what they do is stranger than any machine humans have ever built. Time is not what you think it is. That is not a metaphor. That is a statement of measured fact. The time you experience sitting in your chair right now is different from the time experienced by someone moving relative to you. Not slightly different. Measurably, observably, instrumentally different. If you and a friend synchronized two perfect atomic clocks, the most accurate timekeeping devices ever built, and then your friend took one of those clocks on an aeroplane while you stayed home with the other, when your friend returned, the two clocks would no longer agree. The clock that flew would be behind, not because it malfunctioned, because time itself passed more slowly for it. This is called time dilation, and it is one of the most thoroughly confirmed predictions in all of physics. It is not theoretical, it is not speculative, it happens every single time, and the faster you move, the more dramatic the effect becomes. The equation that governs time dilation is called the Lorentz factor, named after Hendrik Lorentz, the Dutch physicist who derived it in the 1890s while trying to explain why the Michelson-Morley experiment failed to detect the ether. The Lorentz factor is usually written as the Greek letter gamma, and it is calculated by taking 1 and dividing it by the square root of 1 minus your velocity squared divided by the speed of light squared. In plain language, you take your speed, divide it by the speed of light, square that number, subtract the result from 1, take the square root, and then take the reciprocal. The number you get tells you how much time slows down for you relative to someone who is standing still. At low speeds, the Lorentz factor is very close to 1. If you are walking at 3 miles per hour, your Lorentz factor is 1.0000000000000000009. Time is running slower for you than for someone standing still, but the difference is so small that it would take billions of years to accumulate even a single second of disagreement. You will never notice it. Your body will never notice it. Your watch will never notice it. For all practical purposes, time dilation does not exist at walking speed. At 10% of light speed, things start to change. Your Lorentz factor is about 1.005. Time is running 0.5% slower for you than for someone at rest. Still not much. If you traveled at that speed for a year, you would age about 2 days less than someone who stayed home. Noticeable if you had a precise enough clock, but not life-changing. At 50% of light speed, your Lorentz factor is about 1.15. Time is running 15% slower. Travel for a year and you age 10.5 months, while the person at home ages a full year. Now it matters. Now the clocks are visibly out of sync. At 90% of light speed, the Lorentz factor is about 2.3. Time is running less than half as fast for you. 1 year of your time equals 2.3 years for someone standing still. You are aging slower. Not biologically, physically. Every process in your body, every vibration of every atom, every tick of every clock you are carrying, all of it is running at less than half speed compared to the outside world. From your perspective, nothing feels different. Your heartbeat feels normal. Your thoughts proceed at their usual pace, but from the perspective of someone watching you go by, you have become a slow-motion film. At 99% of light speed, the Lorentz factor is about 7. For every year you experience, 7 years pass for the outside world. At 99.9%, the Lorentz factor is 22. At 99.99%, it is 70. The numbers grow without limit as you approach light speed. At exactly light speed, if you could get there, the Lorentz factor would be infinite. Time would stop. 1 second of your experience would correspond to an infinite amount of time passing elsewhere, but you cannot get there, so the case never arises. Time slows down as you speed up, but it never quite stops unless you are a photon, in which case you have no rest mass and the rules are different. This is not philosophy, this is engineering. GPS satellites orbit Earth at about 14,000 kilometers per hour. That is fast by human standards, but it is nowhere near relativistic speeds. It is about 0.00004% of light speed. At that velocity, the Lorentz factor is 1.0000001. Time on the satellite runs about 7 microseconds per day, slower than time on the ground. 7 millionths of a second. That does not sound like much, but GPS works by measuring the time it takes for radio signals to travel from satellites to receivers. Radio signals move at the speed of light. A 7 microsecond error translates to a position error of about 2 kilometers. If engineers did not correct for time dilation, GPS would be useless. Every navigation system in the world would drift off course by several kilometers per day. The corrections are built into the system. Every GPS satellite has a clock that ticks slightly faster than it should to compensate for the fact that time is running slower up there than it is down here. The correction works. GPS is accurate to within a few meters. Time dilation is real, and we are using it to navigate. Muons are subatomic particles created when cosmic rays, high-energy protons from space, slam into the upper atmosphere. A muon is similar to an electron, but about 200 times heavier. Muons are unstable. They decay into an electron and 2 neutrinos with a half-life of about 2.2 microseconds. That means if you start with 1,000 muons, after 2.2 microseconds, you will have about 500 left. After another 2.2 microseconds, you will have 250. The decay is exponential and predictable. Muons are created at altitudes of about 15 kilometers above sea level. From the moment they are created, the clock starts ticking. 2.2 microseconds later, half of them should be gone. Muons move fast, typically around 98% of the speed of light. At that speed, in 2.2 microseconds, a muon can travel about 650 meters. Most muons should decay long before they reach the ground. And yet we detect them. Thousands of muons hit every square meter of Earth's surface every second. They should not be there. By the time they travel 15 kilometers, almost all of them should have decayed. The fact that they make it to the surface is direct evidence of time dilation. From the muon's perspective, time is running normally. Its internal clock says it has been alive for 2.2 microseconds, and it decays as expected. But from Earth's perspective, that muon is moving at 98% of light speed, and its Lorentz factor is about 5. Time is running 5 times slower for the muon than it is for us. What feels like 2.2 microseconds to the muon corresponds to 11 microseconds in our reference frame. In 11 microseconds, traveling at 98% of light speed, a muon can cover about 3 kilometers. Plenty of them make it to the ground. The muon does not live longer because it is special. It lives longer because time itself is passing more slowly for it. The universe is not cheating. The universe is following the rules, and the rules say that time depends on motion. The most famous illustration of time dilation is the twin paradox. It is not actually a paradox. It is a thought experiment designed to make the consequences of relativity impossible to ignore. Imagine 2 twins, Alice and Bob. Alice stays on Earth. Bob gets on a spaceship and accelerates to 99.9% of the speed of light. He travels to a nearby star, turns around, and comes back. From Bob's perspective, the trip takes 1 year. He experiences 1 year of time. His body ages 1 year. His watch ticks forward 1 year. But when he gets back to Earth and steps off the ship, Alice is 22 years older. She has lived through 22 years while Bob lived through 1. Bob is now 21 years younger than his twin. This is not an illusion. This is not a trick of perception. Bob actually aged less. His cells divided fewer times. His heart beat fewer times. He experienced less time. Alice and Bob are no longer the same age, and they never will be again. The reason this is called a paradox is that it seems like the situation should be symmetric. From Bob's perspective, he is stationary, and Alice is the one moving away at 99.9% of light speed. So why does not Alice end up younger? The answer is that the situation is not symmetric. Bob accelerated. Alice did not. Acceleration breaks the symmetry. Special relativity applies to observers moving at constant velocity, and Bob did not move at constant velocity. He sped up, turned around, and slowed down. Those accelerations mean his reference frame is not inertial, and the rules are different for non-inertial frames. The math works out such that Bob is the one who ends up younger, and experiments with atomic clocks on airplanes and satellites have confirmed this over and over. The twin paradox is not a paradox. It is a prediction, and the prediction is correct. Time dilation has a partner. It is called the relativity of simultaneity, and it is even stranger. Two events that happen at the same time in one reference frame do not happen at the same time in another reference frame. Simultaneity is not absolute. There is no universal now. What you call now is different from what someone moving relative to you calls now, and both of you are right. Here is an example. Imagine a train moving past a platform at half the speed of light. You are standing on the platform. On the train, someone is standing in the exact middle of a long car. At the front and back of the car, 2 light bulbs flash at the same instant from the perspective of the person on the train. The light from both bulbs travels toward the middle at the speed of light. Since the person is equidistant from both bulbs, the light from both flashes reaches them at the same time. The person on the train concludes that the 2 flashes were simultaneous. They happened at the same moment. You, standing on the platform, see something different. The train is moving toward you, so the back of the train is moving toward the position where the rear light bulb flashed, and the front of the train is moving away from the position where the front light bulb flashed. From your perspective, the light from the rear bulb has less distance to travel to reach the middle of the train car, because the middle is moving toward it. The light from the front bulb has more distance to travel, because the middle is moving away from it. Both light beams move at the same speed, the speed of light, which is the same for all observers. So, from your perspective, the light from the rear bulb reaches the middle of the car first. That means, from your perspective, the rear bulb must have flashed first. The 2 events were not simultaneous. They happened at different times. Both of you are correct. The person on the train is not wrong. You are not wrong. Simultaneity depends on your reference frame. Events that are simultaneous in one frame are not simultaneous in another frame, moving relative to the first. There is no objective answer to the question of whether the 2 bulbs flashed at the same time. The answer depends on who is asking. This has profound implications. It means the concept of now, the idea that there is a single present moment shared by everyone in the universe, is wrong. Right now, as you are reading this, somewhere in the Andromeda galaxy, 2.5 million light-years away, events are happening. But which events are happening right now? The answer depends on how fast you are moving. If you are sitting still, A certain set of events in Andromeda is happening now. If you start moving toward Andromeda at half the speed of light, a completely different set of events is happening now. Events that were in your future a moment ago are suddenly in your present. Events that were in your present are now in your past. Nothing changed in Andromeda. You just changed your reference frame, and that changed what now means. Space and time are not separate. They are woven together into a single structure called spacetime. This was first clearly articulated by Hermann Minkowski, one of Einstein's former professors, in 1908. Minkowski took Einstein's equations from special relativity and reinterpreted them geometrically. He showed that space and time could be treated as coordinates in a four-dimensional continuum. 3 dimensions of space, 1 dimension of time, combined into a single framework. Events do not happen in space and then in time. They happen at locations in space-time. A point in space-time is called an event, and it is specified by 4 numbers. 3 numbers tell you where it is in space. 1 number tells you when it is in time. Together, those 4 numbers locate the event uniquely in the 4-dimensional fabric of the universe. Minkowski famously declared in a 1908 lecture that henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. He was right. In the framework of relativity, space and time are not independent. How much of your motion through space-time shows up as motion through space, and how much shows up as motion through time depends on your velocity. Everyone moves through space-time at the speed of light. That is a strange sentence, but it is true. If you are sitting still in space, all of your motion through space-time is in the time direction. You are moving forward through time at the maximum rate. If you start moving through space, some of your motion through space-time gets redirected. You are now moving through space as well as through time, which means you are moving through time more slowly. The faster you move through space, the slower you move through time. If you could move through space at the speed of light, all of your motion through space-time would be in the space direction, and none of it would be in the time direction. You would not be moving through time at all. Time would stop. That is what happens to photons. Photons do not experience time. From the perspective of a photon, if such a thing could be said to have a perspective, the moment it is emitted and the moment it is absorbed are the same moment. 0 time elapses. A photon emitted by a star 10 billion light-years away and absorbed by your eye experiences no time between emission and absorption. 10 billion years pass for you. 0 time passes for the photon. This is why nothing with mass can reach the speed of light. If you could reach that speed, time would stop for you. You would not age, you would not think, you would not experience anything, because experience requires time, and at light speed there is no time. The universe does not allow objects with mass to enter that state. The equations prevent it by making the energy cost infinite. The speed of light is not just a speed limit. It is the boundary between motion through time and motion through space. Cross that boundary and you stop being a thing that experiences time. You become a thing that exists timelessly, a frozen instant stretched across space. Photons live there. You do not. You are stuck on this side of the line, where time exists and motion has consequences. The speed of light also protects causality. Causality is the principle that cause precedes effect. If you drop a glass, it falls and then it breaks. The falling causes the breaking. The breaking does not cause the falling. The order matters, and in a universe where time is absolute, the order is obvious. But in a universe where time is relative, where simultaneity depends on reference frame, causality becomes fragile. If events can be simultaneous in one frame and sequential in another frame, what stops cause and effect from reversing? What stops you from observing an effect before its cause? The speed of light stops it. Information cannot travel faster than light. Cause and effect are linked by signals, and those signals propagate at the speed of light or slower. If you could send information faster than light, you could set up a scenario where the effect arrives before the cause in some reference frames. You could, in principle, send a signal into your own past. That would break causality. It would create paradoxes. The universe does not allow it. The speed of light is the speed limit, not just for matter, but for information. Nothing can carry a signal from one point in spacetime to another faster than light can. That includes gravity. If the sun suddenly disappeared, Earth would continue orbiting for about 8 minutes, the time it takes light to travel from the sun to Earth, before the change in the gravitational field reached us. Gravity propagates at the speed of light. Cause and effect are bound by the same limit. The structure of spacetime enforces this. In Minkowski spacetime, every event has a light cone. The light cone divides spacetime into 3 regions. The future light cone contains all events that can be affected by the original event. The past light cone contains all events that can affect the original event, and the region outside both cones contains events that are causally disconnected from the original event. No signal from the original event can ever reach those events, and no signal from those events can ever reach the original event. The light cones are set by the speed of light. Move faster than light, and you escape your light cone. You reach events that are causally disconnected from your starting point. You violate causality. The universe does not let that happen. The speed of light is the edge of the light cone, and the light cone is the boundary of what can influence what. Time is not a river flowing at a constant rate. Time is a coordinate in spacetime, and how fast you move through it depends on how fast you move through space. The faster you go, the slower time passes for you. The closer you get to the speed of light, the closer time gets to stopping. At exactly the speed of light, time stops entirely. That is where photons live. That is the boundary. And everything in the universe, every particle, every force, every interaction respects that boundary. Not because the universe is polite, because the math does not work any other way. Einstein did not invent time dilation, he derived it. He showed that if the speed of light is constant for all observers, then time and space cannot be absolute. They have to bend, flex, and adjust to keep the speed of light the same in every reference frame. The bending is real, the flexing is measurable, and the adjustment happens every time anything moves. You are experiencing time dilation right now. It is unimaginably small because you are moving unimaginably slowly compared to light, but it is there. Your time is not the same as the time experienced by a satellite overhead, or a particle in the LHC, or a photon crossing the galaxy. Everyone has their own time, and all of those times are related by the speed of light. The speed of light is not just the speed of light, it is the structure of spacetime made visible. It is the rule that connects space to time. It is the reason causality works, and the reason nothing can travel backward into its own past. And it is the reason particles at the LHC can never quite reach that last fraction of a percent. Because reaching it would mean stopping time, and time does not stop for things with mass. The universe has rules. This is one of them. And every experiment ever conducted has confirmed it. But knowing that light speed is a limit and understanding why light moves at that speed in the first place are two different questions. Einstein told us what happens when you approach the speed of light. He did not tell us why light moves at that speed to begin with. That answer would come later, from a different direction, from a physicist who was less interested in spacetime and more interested in what light actually does when it travels. His name was Richard Feynman, and his explanation would turn out to be even stranger than Einstein's. Richard Feynman was born in 1918 in Queens, New York. By the time he was in high school, he was fixing radios for neighbors and teaching himself calculus from library books. By the time he was at MIT, he was already solving problems that stumped his professors. During World War II, he worked on the Manhattan Project at Los Alamos, where he spent his free time cracking safes and playing bongos. After the war, he joined the faculty at Cornell University and started thinking seriously about light. The problem he was trying to solve was not relativity. Relativity worked. Einstein had already figured that out. The problem was quantum mechanics. Light, according to quantum mechanics, was both a wave and a particle. That statement is usually presented as if it makes sense. It does not. Waves spread out through space. Particles are localized. Waves interfere with each other. Particles collide. Waves do not have definite positions. Particles do. Light behaves like a wave when you are not looking at it, and like a particle when you are. That is not a metaphor. That is what the experiments show, and nobody in the early 20th century could explain why. The wave nature of light was settled science by the 1800s. Thomas Young's double-slit experiment in 1801 proved that light creates interference patterns, bright and dark bands, that only make sense if light is a wave. Shine light through two narrow slits, and you get alternating bright and dark fringes on a screen behind the slits. The bright fringes are where the waves from both slits arrive in phase and reinforce each other. The dark fringes are where the waves arrive out of phase and cancel each other out. Waves do that. Particles do not. Except light also does things particles do. In 1905, the same year Einstein published his paper on special relativity, he published another paper explaining the photoelectric effect. When light shines on certain metals, it knocks electrons out of the surface. Classical wave theory predicted that brighter light should knock out electrons with more energy. It did not. Dim light of the right color knocked out high-energy electrons. Bright light of the wrong color knocked out nothing. The energy of the ejected electrons depended only on the color of the light, which corresponds to its frequency, not on its intensity. Einstein explained this by proposing that light was made of discrete packets of energy he called quanta. Later, those quanta were called photons. A photon carries an amount of energy equal to Planck's constant times its frequency. High-frequency light, like blue or ultraviolet, carries high-energy photons. Low-frequency light, like red or infrared, carries low-energy photons. The number of photons determines the brightness, but the energy per photon determines what happens when one of them hits an electron. That is particle behavior. Waves do not come in packets, particles do. By the 1920s, physicists were stuck with two incompatible descriptions of light, and both of them worked depending on what experiment you ran. Wave-particle duality became the accepted explanation, which is another way of saying nobody understood what was going on, but everyone agreed the math worked. Matter turned out to have the same problem. Electrons, which everyone assumed were particles, produced interference patterns in diffraction experiments. Fire electrons one at a time through a double slit, and each electron hits the screen at a single point, like a particle. But over time, the individual hits build up into an interference pattern, like a wave. Each electron somehow passes through both slits at once and interferes with itself. That should be impossible. It happens anyway. The standard interpretation of quantum mechanics, developed by Niels Bohr and Werner Heisenberg in the late 1920s, said that particles do not have definite positions or velocities until you measure them. Before measurement, a particle exists in a superposition of all possible states simultaneously. The act of measurement collapses the superposition into a single definite outcome, but you cannot predict which outcome you will get. You can only calculate probabilities. Bohr called this the Copenhagen interpretation, and it became the orthodox view. It was also deeply unsatisfying. Einstein hated it. He spent the rest of his life arguing that quantum mechanics was incomplete, that there had to be some deeper layer of reality underneath the probabilities. He never found it. Feynman did not care about philosophy. He cared about calculation. In the early 1940s, physicists were trying to develop a quantum theory of electromagnetism, a framework that could describe how light and matter interacted at the quantum level. Classical electromagnetism, Maxwell's equations, worked beautifully for large-scale phenomena like radio waves and electric circuits. But at the scale of atoms and electrons, classical theory broke down. When you tried to calculate the behavior of an electron interacting with light using the tools of quantum mechanics available at the time, you got nonsense. The equations produced infinities, not large numbers, infinite numbers, infinite energy, infinite mass, infinite charge. The math stopped working. Several physicists, including Julian Schwinger and Shinichiro Tominaga, were working on the problem independently. Feynman approached it differently. He threw out most of the existing formalism and started from scratch. In 1941, inspired by a remark Paul Dirac had made in a 1932 paper, Feynman developed a new way of thinking about quantum mechanics. He called it the path integral formulation, though it is more commonly known as the sum over histories approach. The idea is simple in concept and bizarre in implication. In classical mechanics, a particle has a trajectory. You throw a ball and it follows a parabola. The path is determined by the initial conditions and the forces acting on it. In quantum mechanics, Feynman said, the particle does not follow a single path, it follows all possible paths simultaneously. Every path from the starting point to the ending point, no matter how absurd, contributes to the final result. The particle might go in a straight line, it might spiral, it might loop backward, take a detour through Jupiter, and arrive at the destination from the opposite direction. All of those paths happen, every single one, and each path contributes a number called a probability amplitude. Probability amplitudes are complex numbers, numbers that have both a magnitude and a phase. The phase is an angle, and it determines whether the contribution from a given path adds constructively or destructively to the total. When you add up the amplitudes from all possible paths, most of them cancel out. The wildly looping paths have phases that vary rapidly and interfere destructively with each other. The paths that are close to the classical trajectory, the path Newton would have predicted, have similar phases and interfere constructively. The result is that the most probable outcome is the classical path, but the other paths do not disappear. They are still there, contributing tiny corrections that show up in precise experiments. This is not a metaphor. This is how quantum mechanics works according to Feynman's formulation. When a photon travels from a light source to your eye, it does not take the straight line path. It takes every path. Most of those paths cancel out when you add up the amplitudes. The straight line path and the paths very close to it survive the cancellation and dominate the final answer. That is why light appears to travel in straight lines most of the time. It is not because photons are following straight lines. It is because the curved paths cancel each other out. Feynman loved to illustrate this with a thought experiment involving a mirror. You look at yourself in a mirror and you see your reflection. Light from your face travels to the mirror, bounces off, and enters your eye. Classical optics says the light hits the mirror at a specific point, the point where the angle of incidence equals the angle of reflection. That is the shortest path, the path light takes according to classical theory. But quantum mechanics says light does not just reflect off that one point. It reflects off every point on the mirror. Light from your face hits the top of the mirror, the bottom, the left edge, the right edge, and every point in between. All of those reflections contribute. Most of them cancel out because the paths have different lengths, and the probability amplitudes end up out of phase. The region of the mirror near the classical reflection point has paths that are all roughly the same length, so the amplitudes add constructively. That region dominates the reflection. But if you carefully block off parts of the mirror, you can see interference effects that prove the light was using the whole surface, not just the center. This was not just a reinterpretation, it was a new way of calculating. Feynman developed a graphical tool to keep track of all the possible ways particles could interact. He drew diagrams, simple pictures with lines and vertices representing particles and interactions. A straight line with an arrow represented an electron moving forward in time. A wavy line represented a photon. A point where lines met represented an interaction, an event where particles collided, or a photon was emitted or absorbed. These diagrams, which everyone now calls Feynman diagrams, became the standard language of particle physics. They are not just illustrations. Each diagram corresponds to a specific mathematical term in the calculation of a probability amplitude. Add up all the diagrams, and you get the total amplitude for the process you are trying to calculate. The theory Feynman was building became known as quantum electrodynamics, usually abbreviated QED. It describes how light and matter interact at the quantum level. An electron sitting in space does not just sit there, it is constantly emitting and absorbing photons. Those photons are called virtual particles because they do not last long enough to be directly observed. They pop into existence, travel a short distance, and get reabsorbed. The electron is surrounded by a cloud of virtual photons flickering in and out of existence. When two electrons come near each other, they interact by exchanging virtual photons. One electron emits a photon, the other electron absorbs it. That exchange carries momentum from one electron to the other, and the result is the electromagnetic repulsion we call the Coulomb force. The force is not a mysterious action at a distance, it is photons being traded back and forth. Virtual particles sound like a cheat. They sound like math tricks invented to make the equations work. They are not. Virtual particles have measurable effects. One of the most famous is the Lamb shift. In 1947, Willis Lamb measured the energy levels of hydrogen atoms with extraordinary precision and found a tiny discrepancy between the observed energies and the energies predicted by the existing quantum theory. The difference was small, but it was real. Feynman and others used QED to calculate the effect of virtual photons on the electron's energy, and the calculation matched Lamb's measurement almost exactly. The virtual photons were doing something. They were shifting the energy levels of the atom by a measurable amount. QED was not just a theory, it was a tool that worked. Another prediction of QED is the electron's magnetic moment. Classical physics predicts a certain value. Quantum mechanics adds a small correction. QED adds an even smaller correction due to virtual particles. The calculation involves summing over thousands of Feynman diagrams, each representing a different way virtual particles can pop in and out of existence around the electron. The final answer agrees with experiment to more than 10 decimal places, 10. That is 1 part in 10 billion. QED is the most precisely tested theory in the history of physics. Nothing else comes close, but QED did more than make accurate predictions. It explains something fundamental about the speed of light. Light does not move at 299 million meters per second because someone set a dial. It moves at that speed because that is the rate at which photons propagate through space when they interact with the electromagnetic field. The speed of light is a property of the photon-electron interaction. It is built into the structure of quantum electrodynamics, the way the rules of chess are built into the board. You cannot change it without changing the theory, and the theory is constrained by symmetries and conservation laws that do not leave room for adjustment. The speed of light appears in Maxwell's equations as a constant that relates the strength of electric fields to the strength of magnetic fields. In QED, that constant emerges from the way photons couple to charged particles. The coupling strength, called the fine structure constant, is a dimensionless number approximately equal to 1 divided by 137. That number determines how strongly electrons interact with photons. It sets the rate at which photons are emitted and absorbed. And because photons are the carriers of electromagnetic interactions, the speed at which they propagate sets the speed at which electromagnetic influences spread through space. That speed is c. It is not imposed from outside. It is a consequence of the interaction dynamics. Feynman once described this in a lecture. He said, "An electron does not follow a single path from one point to another. It explores all possible paths, including paths that involve emitting and reabsorbing photons, interacting with virtual particles, even briefly creating particle-antiparticle pairs that vanish almost immediately. The sum of all those contributions gives you the observed behavior of the electron." And the same thing applies to photons. A photon does not travel from point A to point B along a single trajectory. It takes every possible route. Most of those routes cancel out. The ones that survive are the ones that propagate at the speed of light, not because photons are forbidden from going slower or faster, because the probability amplitudes for paths at other speeds interfere destructively and vanish. The speed of light is what is left after the cancellation. This is a profoundly different picture from the one most people carry around. Light does not move at c because there is a cosmic speed limit sign posted somewhere in the fabric of space. Light moves at c because that is the speed that survives when you add up all the possible ways a photon can get from one place to another. The universe is not enforcing a rule. The universe is doing a calculation, and the answer to that calculation is 299,792,458 meters per second. Feynman's approach was controversial at first. His diagrams looked like doodles. His path integral formulation seemed like it was replacing one set of infinities with another. But the predictions worked, and eventually other physicists proved that Feynman's method was mathematically equivalent to the approaches Schwinger and Tomonaga had developed independently. All three of them shared the Nobel Prize in Physics in 1965 for their work on quantum electrodynamics. Feynman's version became the most widely used because the diagrams made the calculations easier to visualize and organize. You could look at a Feynman diagram and immediately see what physical process it represented. You could add more diagrams to account for higher-order corrections. You could build up the full answer piece by piece, each piece corresponding to a picture you could draw on a napkin. Feynman spent the rest of his career developing and extending QED. He applied the path integral formulation to other areas of physics. He worked on the theory of superfluidity. He contributed to the development of quantum chromodynamics, the theory of the strong nuclear force. He became famous not just as a physicist, but as a teacher. His lectures at Caltech in the early 1960s were recorded and published as the Feynman Lectures on Physics, which became one of the most widely read physics textbooks ever written. In 1985, he published a short book called QED, The Strange Theory of Light and Matter, based on a series of public lectures he gave in New Zealand. The book explained quantum electrodynamics to a general audience without using equations. It is still in print. It is still strange. What Feynman discovered was not a new speed limit. Einstein had already found that. What Feynman discovered was the mechanism underneath the limit. Light moves at c because photons are massless excitations of the electromagnetic field, and the field's properties, encoded in the equations of quantum electrodynamics, determine how fast those excitations propagate. The speed is fixed by the coupling constant, the permittivity and permeability of free space, and the structure of the theory itself. Change any of those, and you are no longer describing electromagnetism. You are describing something else. The speed of light is not arbitrary. It is a consequence of the forces that govern how light and matter interact, and those forces do not operate the way common sense suggests. Particles do not follow single paths, they follow all paths. Interactions do not happen at single points in time. They happen across all possible moments, weighted by probability amplitudes that interfere with each other. The universe at its smallest scales is not a clockwork mechanism. It is a vast, ongoing calculation where every possible outcome contributes to the result, and most of them cancel out, leaving behind only the behaviors we observe. The speed of light is the output of that calculation. It is the number that falls out when you sum over all possible histories and take seriously the idea that quantum mechanics is not just a tool for making predictions, but an accurate description of how reality actually works. Feynman himself was uncomfortable with some of the implications. He once said that nobody understands quantum mechanics. That was not modesty, that was honesty. The math works. The predictions are confirmed to absurd precision. But the picture it paints of reality is so far removed from everyday experience that even the people who invented the theory find it unsettling. Particles are not little billiard balls. They are probability amplitudes smeared across space-time. Light is not a beam traveling through space. It is a superposition of every possible path between emission and absorption. And the speed of light is not something light does. It is something light is. It is the rate at which information propagates when carried by massless particles in a universe governed by the equations of quantum field theory. By the time Feynman finished developing QED, the speed of light was no longer just a constant you plugged into equations. It was a derived quantity. It emerged naturally from the theory. And that raised a new question. If the speed of light is a consequence of quantum interactions, then what else is a consequence? What other features of reality are not fundamental but emergent, side effects of deeper rules operating at scales we cannot directly observe? The answers would require pushing quantum field theory even further. They would require thinking of the universe itself not as a stage where events happen, but as a computational process, a grand sum over all possible histories, unfolding one interaction at a time according to rules that allow for no exceptions and no shortcuts. Feynman had opened the door. What lay beyond it was even stranger than what he had found. Feynman had opened the door. What lay beyond it was even stranger than what he had found. Because quantum electrodynamics, The theory he spent years building turned out to be more than just a framework for calculating how light and matter interact. It turned out to be the most accurate scientific theory ever constructed. Not close to accurate, not impressively accurate. Accurate to a degree that borders on the absurd. Accurate in ways that make you wonder whether the universe is running on mathematics, or whether mathematics is just the language we use to describe something even deeper. Here is the number that makes physicists lose sleep in a good way. The electron's magnetic moment, a property that describes how an electron behaves in a magnetic field, has been measured experimentally to 12 decimal places. 12. The measured value is 1.001159652181. Quantum electrodynamics predicts that the value should be 1.001159652182. Those numbers agree for 12 digits. The disagreement, if you can call it that, does not show up until the 13th digit. The theory and the experiment match to better than 1 part in a trillion. That is not normal. Most scientific theories are good to a few decimal places if you are lucky. Newton's laws work beautifully for launching satellites and landing rovers on Mars, but they are approximations. They break down at high speeds and in strong gravitational fields. General relativity is more accurate, but even general relativity has not been tested to 12 decimal places. The standard model of particle physics, which includes quantum electrodynamics as one of its components, is extraordinarily successful, but most of its predictions are tested to 3 or 4 significant figures, maybe 5 if the experiment is exceptionally clean. 12 digits is not incremental progress. It is a different category of precision. It is the kind of precision that suggests the theory is not just approximately right. It is exactly right, at least within the domain where it applies. Richard Feynman called quantum electrodynamics the jewel of physics. He was not exaggerating. QED describes how electrically charged particles, primarily electrons, interact with light. It treats light as photons, quantized packets of electromagnetic energy, and it treats electrons as excitations of an electron field that permeates all of space. When an electron emits a photon, the electron field loses energy and the electromagnetic field gains energy. When an electron absorbs a photon, the reverse happens. The two fields are coupled, linked by an interaction term in the equations that allows energy to flow back and forth between them. That coupling is what produces every electromagnetic phenomenon in the universe: light bulbs, lasers, the fact that solid objects do not pass through each other, the colors you see, the warmth you feel from sunlight. All of it is electrons and photons exchanging energy according to the rules of QED. The theory does not just predict the existence of these interactions, it calculates their strength with ludicrous precision. Take the anomalous magnetic moment of the electron. Classical physics predicts a magnetic moment of exactly 2 Bohr magnetons, a unit named after Niels Bohr. Quantum mechanics, without QED, adds a small correction due to the electron's spin and predicts a value slightly larger than 2. QED goes further. It accounts for the fact that electrons are not isolated. They are surrounded by a seething cloud of virtual particles, photons that pop into existence, exist for a tiny fraction of a second, and then vanish. Those virtual photons affect the electron's magnetic moment. Calculating the effect requires summing over every possible way a virtual photon can be emitted and reabsorbed, every possible path the photon can take, every possible energy and momentum it can carry. Each possibility is a Feynman diagram. Each diagram contributes a term to the final answer. Add them all up and you get the anomalous magnetic moment. The first-order correction, the simplest diagram where the electron emits and reabsorbs a single photon, gives a correction of about 0.00116. That is already close to the measured value. Higher order corrections, diagrams with 2 photons, 3 photons, loops within loops, add smaller and smaller contributions. By the time you account for diagrams with up to 5 loops, which involves summing over thousands of individual terms, the prediction matches the measurement to those 12 decimal places. The calculation is not simple. Each additional loop makes the math exponentially harder. Some of the most recent calculations required supercomputers running for months. But the answer that comes out matches what happens in the lab, every time, without fail. Another landmark result is the Lamb shift. In the late 1940s, Willis Lamb and Robert Rutherford measured the energy levels of hydrogen atoms using microwave spectroscopy. According to the quantum theory of the time, developed by Paul Dirac in the 1920s, 2 particular energy levels in hydrogen, labeled 2s1/2 and 2p1/2, should have been identical. They were not. Lamb measured a tiny difference, about 1 part in 10 million of the total energy. That difference is now called the Lamb shift, and it earned Lamb the Nobel Prize in 1955. The shift exists because the electron in a hydrogen atom is not sitting in a smooth, empty vacuum. It is sitting in a vacuum filled with virtual particles. Virtual photons flicker in and out of existence around the electron. Virtual electron-positron pairs appear and disappear. Those virtual particles create a kind of quantum static that shifts the energy levels slightly. QED predicts the size of that shift, and the prediction matches Lamb's measurement. The Lamb shift was more than just another successful prediction. It was proof that the vacuum is not empty. Empty space, according to quantum field theory, is not a blank stage where particles perform. It is an active participant. The vacuum has structure, it has energy, it fluctuates. And those fluctuations have measurable effects on real particles. The electron in a hydrogen atom feels the vacuum around it, and that changes its energy. You cannot ignore the vacuum and get the right answer. The vacuum matters. In 2022, scientists at the Max Planck Institute for Nuclear Physics in Heidelberg pushed the precision of QED tests even further. They measured the magnetic moments of 2 isotopes of neon, neon-20 and neon-22, and compared the results. The difference between the 2 magnetic moments depends on the structure of the nucleus, which QED does not directly describe, but the absolute values of the magnetic moments depend on QED corrections. By comparing isotopes, the team was able to isolate the QED contribution and test it to 13 decimal places, 100 times more precise than previous measurements in similar systems. QED passed. Again. The theory works because it is built on a framework that takes quantum mechanics and special relativity seriously at the same time. Quantum mechanics says particles are waves, probabilities, superpositions. Special relativity says space and time are intertwined and the speed of light is constant. Combining those 2 ideas is not trivial. Early attempts produced infinities, energies that blew up to infinity, probabilities that made no sense. Feynman, Julian Schwinger, and Shinichiro Tominaga independently figured out how to tame the infinities using a technique called renormalization. The idea is that the bare properties of particles, their mass and charge before any interactions are taken into account, are not the properties you measure in the lab. What you measure is the dressed properties, the mass and charge after accounting for the cloud of virtual particles surrounding every real particle. The bare values can be infinite, but the infinities cancel out in a controlled way, leaving finite measurable quantities that match experiment. Renormalization sounds like a trick. It is not. It is a systematic procedure for separating the physics you care about from the physics you do not. The infinities that show up in the raw calculations are artifacts of pretending that particles are point-like objects with no internal structure. Real particles are not points. They are excitations of fields, and fields have correlations at all distance scales. When you measure an electron's charge, you are not measuring the charge of a geometrical point. You are measuring the effective charge after accounting for all the virtual particles that screen and modify the interaction. Renormalization organizes that accounting. It allows you to express the final answer in terms of quantities you can measure in the lab, like the electron's mass and charge, rather than quantities that depend on details of the theory at arbitrarily high energies where the theory might not even apply. The success of renormalization turned quantum electrodynamics into a prototype. Every modern quantum field theory uses the same basic structure. You start with fields, add interaction terms, calculate Feynman diagrams, sum over all possible processes, renormalize the infinities, and out comes a prediction. The standard model of particle physics is built this way. The theory of the weak nuclear force, which describes radioactive decay, is a renormalizable quantum field theory modeled on QED. The theory of the strong nuclear force, which holds quarks together inside protons and neutrons, is a renormalizable quantum field theory modeled on QED. QED was the proof of concept. It showed that quantum field theory works, and it set the template for everything that came after. But QED is not just a calculational tool, it is a statement about how reality operates. According to QED, every interaction between light and matter happens because electrons and photons are constantly emitting and absorbing each other. An electron sitting by itself does not just sit there, it emits a photon and recoils. The photon travels a short distance and gets reabsorbed. The electron emits another photon. That photon gets reabsorbed. This process never stops. The electron is surrounded by a flickering cloud of virtual photons that appear and disappear faster than anything can measure directly. Those photons are not real in the sense that you can catch one and put it in a detector. They are virtual. They exist only as intermediate steps in a calculation. But their effects are real. They shift energy levels. They alter magnetic moments. They produce measurable forces. When two electrons come near each other, they repel. Classical electromagnetism says the repulsion is caused by the electric field one electron creates and the other electron responds to. QED says something different. The repulsion is caused by the two electrons exchanging virtual photons. One electron emits a photon, the other absorbs it. The exchange transfers momentum, and that momentum transfer is what we call the electromagnetic force. The force is not a field acting at a distance. The force is particles being thrown back and forth. Photons are the messenger particles of electromagnetism. Every time you feel an electromagnetic force, you are feeling the cumulative effect of countless virtual photons being traded between charged particles. This is where the speed of light enters the picture in a deeper way than Einstein's relativity alone suggests. Photons are massless. That is not an assumption. It is a consequence of the gauge symmetry underlying electromagnetism, a mathematical property of Maxwell's equations that survives the transition to quantum field theory. Massless particles always move at the speed of light. They have no rest frame. They cannot be brought to a stop. From the moment they are created to the moment they are destroyed, they move at c. That is the only speed available to them. And because photons are the carriers of electromagnetic interactions, the speed at which electromagnetic influences propagate is also c. The electromagnetic force does not act instantaneously, it propagates at light speed. If you move an electron, the change in the electromagnetic field spreads outward at the speed of light. An electron a meter away feels the change 1 meter divided by c seconds later. That delay is not a transmission time in the sense of information traveling through a medium. It is the rate at which the field itself updates. The speed of light, in this framework, is the rate at which causality operates. Cause and effect are linked by the exchange of particles, and those particles propagate at c if they are massless, or slower than c if they have mass. Information cannot travel faster than light because information is carried by particles, and particles obey the rules of quantum field theory, and those rules do not allow faster than light propagation. The speed of light is the clock speed of the universe. It is the rate at which interactions happen, the rate at which fields respond to changes, the rate at which one event can influence another. This is not a limit imposed from outside, it is a property of the interaction itself. Quantum field theory is built on the principle of locality. Interactions happen at points in spacetime. A particle at one location can only directly affect a particle at the same location. If you want to influence something far away, you have to send a messenger particle. That particle travels from here to there, and the speed at which it travels is determined by its mass. Massless particles travel at c. Massive particles travel slower. The speed of light is the maximum speed because it is the speed of massless particles, and there is nothing faster than massless. You cannot have a particle with negative mass. The equations do not allow it. So c is the top speed, not because nature forbids faster speeds, because there is no mechanism within quantum field theory that produces faster speeds. The speed of light is what you get when you remove all impediments to motion. It is the default speed, the speed at which the universe operates when nothing is slowing it down. Feynman once described quantum field theory as a kind of computation. The universe, he said, is constantly calculating. Every possible way an interaction can happen contributes to the final outcome. Most of those ways cancel out. The ones that survive are the ones we observe. This is the path integral in action. The universe is not choosing which path to take. It is taking all of them simultaneously, and the sum of all those paths is reality. The probabilities we calculate are not guesses about what the universe might do. They are the output of a calculation the universe is actually performing. Every interaction, every emission, every absorption, every decay is a term in that calculation. And the calculation happens at the speed of light because that is the rate at which the terms update. This perspective makes the speed of light less mysterious and more inevitable. It is not a cosmic speed limit in the sense of a rule imposed on motion. It is the rate at which quantum fields propagate. Fields do not sit still. They fluctuate, they interact, they transfer energy from one location to another. And the rate at which that transfer happens is determined by the properties of the field. For the electromagnetic field, that rate is c. For the strong nuclear field, the field that binds quarks into protons, the rate is also c, because the gluons that carry the strong force are massless like photons. For the weak nuclear field, the rate is slower because the W and Z bosons that carry the weak force have mass. Massive particles travel slower than c, so weak interactions propagate slower than electromagnetic interactions. But the upper limit, the ceiling, is still c. No field propagates faster. No interaction happens faster. The speed of light is the universal rate. Quantum electrodynamics has been tested in more ways than almost any other theory in physics. It predicts the scattering cross-sections of electrons and photons, the rates at which particles collide and scatter off each other. It predicts the lifetimes of excited atomic states, how long an atom stays in a high-energy configuration before emitting a photon and dropping to a lower energy. It predicts the spectrum of light emitted by atoms, the specific colors that show up when you heat an element and look at the light it produces. Every prediction matches experiment. The agreement is not approximate, it is exact within the measurement uncertainty. Some measurements, like the electron's magnetic moment, push the uncertainty down to parts per trillion. QED matches them all. There are limits to QED. The theory is not complete. It describes electromagnetism, but it does not describe the weak nuclear force or the strong nuclear force or gravity. It works at low energies, but at extremely high energies, the coupling constant, the number that measures the strength of the electromagnetic interaction, starts to grow. If you push the energy high enough, hypothetically, the coupling constant diverges to infinity at a point called the Landau pole. That is a sign that QED by itself is not well defined at arbitrarily high energies. Most physicists interpret this as evidence that QED is part of a larger theory, probably a grand unified theory that combines electromagnetism with the other forces. At everyday energies, even at the energies accessible in particle colliders, the Landau pole is far away and irrelevant. QED works perfectly, but it hints that there is more structure above it. Another puzzle is the cosmological constant problem. QED predicts that empty space should have energy due to the vacuum fluctuations of all the quantum fields permeating the universe. You can calculate how much energy the vacuum should have by summing over all possible virtual particles. The answer you get is enormous, roughly 120 orders of magnitude larger than the observed energy density of the universe. That discrepancy is sometimes called the vacuum catastrophe, and it is one of the biggest unsolved problems in physics. QED gives the wrong answer for the vacuum energy, and no one knows why. The most likely explanation is that there is some mechanism, not yet understood, that cancels most of the vacuum energy, leaving behind the tiny amount we observe as dark energy. But that mechanism is not part of QED. It would have to come from a more complete theory, possibly involving quantum gravity. Despite those limitations, QED remains the gold standard for what a physical theory should be. It is mathematically consistent. It is experimentally verified to absurd precision. It makes clear, testable predictions. And it fits into a broader framework, the Standard Model, that describes all known particles and forces except gravity. QED is not just accurate, it is a model for how to think about forces and particles. It shows that forces are not mysterious influences acting at a distance, they are exchanges of particles. It shows that particles are not little spheres bouncing around, they are excitations of fields. And it shows that the speed of light is not an arbitrary constant. It is the rate at which massless fields propagate, the rate at which information moves through spacetime, the rate at which the universe computes the next moment from the current moment. That last point is worth sitting with. If quantum field theory is a computation, then the speed of light is the clock speed. It is the rate at which the universe updates. Every interaction, every change, every event happens at a rate determined by how fast massless particles can carry information from one place to another. Slower than that, and you are dealing with massive particles which take longer to propagate. Faster than that, and you are violating causality, which the universe does not allow. The speed of light is the speed at which now becomes the next moment. It is the speed at which cause leads to effect. It is the speed at which reality happens. Feynman did not phrase it that way. He was too careful to make grand metaphysical claims, but the structure of QED points in that direction. If you take the equations seriously, if you believe that Feynman diagrams are not just calculational tools but representations of what actually occurs, then every photon emitted and absorbed, every virtual particle that flickers into and out of existence, every interaction vertex in every diagram is a piece of the computation. And the computation runs at the speed of light, because that is the speed at which the electromagnetic field updates. The universe is not sitting still and then suddenly jumping to a new configuration. It is evolving continuously, and the rate of that evolution is set by c. This brings us back to the question of motion. If the speed of light is the rate at which the universe updates, then what happens to an object moving at the speed of light? What happens to time for that object? What happens to its experience of the universe? The equations of relativity say time stops, the Lorentz factor diverges. From the perspective of a photon, no time passes. From the perspective of an outside observer, the photon is moving through space at the maximum possible speed. Both perspectives are correct, but the implications are unsettling. Because if time stops at the speed of light, then the speed of light is not just the upper limit on velocity. It is the edge of time itself. It is the boundary between things that experience duration and things that do not. And that boundary is built into the structure of spacetime and enforced by the interactions described in quantum electrodynamics. The speed of light is not a rule, it is a consequence of how fields propagate, how particles interact, and how the universe computes the next moment from the present. And once you see it that way, the question is not why nothing can go faster than light. The question is, what does it mean to move at light speed, and what does it mean that most of the universe cannot? This brings us back to the question of motion. If the speed of light is the rate at which the universe updates, then what happens to an object moving at the speed of light? What happens to time for that object? What happens to its experience of the universe? The equations of relativity say time stops, the Lorentz factor diverges. From the perspective of a photon, no time passes. From the perspective of an outside observer, the photon is moving through space at the maximum possible speed. Both perspectives are correct, but the implications are unsettling, because if time stops at the speed of light, then the speed of light is not just the upper limit on velocity. It is the edge of time itself. Let's walk through what actually happens as you approach the speed of light, step by step, because this is where intuition breaks down completely and the math becomes the only guide you have left. At rest, sitting in your chair, your Lorentz factor is exactly 1. Time passes for you at the maximum rate. Every second you experience is 1 second of coordinate time, the time measured by clocks in the universe around you. You and the universe are in sync. Now imagine you start moving, not walking, not driving, moving at a significant fraction of the speed of light. At 10% of light speed, your Lorentz factor is about 1.005. Time is running 0.5% slower for you, still barely noticeable. At 50%, it is 1.15. Time has slowed by 15%. That is when you start to feel it, not in your body, but in the clocks. You age 10.5 months, while someone at rest ages a full year. The gap is real and measurable. At 90% of light speed, time for you is running at less than half the rate it runs for someone standing still. Your Lorentz factor is 2.3. 1 year of your experience equals 2.3 years of theirs. At 99%, the factor jumps to 7. At 99.9%, it is 22. At 99.99%, 70. The numbers climb faster and faster. At 99.999%, the Lorentz factor is about 700. You could travel for what feels like a year, and 700 years would pass in the rest of the universe. Your family would be dead. Your civilization would be history. The stars you left behind would have drifted into new configurations, and from your perspective, nothing unusual happened. Your heartbeat felt normal. Your thoughts proceeded at their usual pace. Time did not feel slower. It simply was slower relative to everything you left behind. Keep going. Push closer to the speed of light. At 99.9999%, 6 nines after the decimal, the Lorentz factor is about 7,000. 1 year for you, 7,000 years for the universe. Civilizations rise and fall while you blink. At 7 nines, the factor is 22,000. At 8 nines, 70,000. The curve is not linear, it is asymptotic. Every additional 9 you add makes the Lorentz factor explode by roughly another factor of 3. There is no upper limit. The closer you get to light speed, the more extreme the time dilation becomes. And at exactly the speed of light, the Lorentz factor is infinite. Time does not run slowly, time stops. That is not a metaphor. That is the prediction, the equations of special relativity, the ones that have been tested to absurd precision in particle accelerators and atomic clocks and GPS satellites, say that at exactly the speed of light, proper time, the time experienced by the object, drops to 0. If you could somehow reach light speed, which you cannot, you would experience 0 duration between departure and arrival, no matter how far you traveled. A journey across the galaxy would take you no time. A journey across the universe would take you no time. The moment you started moving would be the same moment you arrived. From your perspective, the trip would be instantaneous. No waiting, no travel time. No experience of motion. Just departure and arrival collapsed into a single event. From the perspective of someone watching you, the situation looks different. They see you moving at the speed of light. They see you crossing space. It takes you time to get from one place to another. If you travel 1 light year, it takes you 1 year from their perspective. If you travel 1 billion light years, it takes you 1 billion years. But for you, 0 time passes. The universe ages. You do not. That is the trade. As you approach the speed of light, you trade time for space. You move through space faster and faster, and in exchange, you move through time slower and slower. At exactly the speed of light, all of your motion is through space, and none of it is through time. You have traded away time entirely. Photons live in this state. A photon emitted by a star 1 billion light-years away travels for 1 billion years from the perspective of an observer on Earth. But from the photon's perspective, if you can even call it a perspective, no time passes. The moment the photon is emitted is the same moment it is absorbed. There is no journey, there is no duration. The photon does not experience the passage of time because time does not pass for it. It exists in a single frozen instant that spans 1 billion light-years of space. The universe around it ages. The photon does not. This is why photons do not have a rest frame. A rest frame is a reference frame where an object is stationary. For objects with mass, you can always find a rest frame. No matter how fast you are moving relative to me, there is some reference frame where you are sitting still. But for a photon, there is no such frame. If you try to construct a reference frame where a photon is at rest, the equations break down. The Lorentz transformation, the set of equations that converts measurements from one reference frame to another, becomes undefined. Division by 0, infinities. The math stops working. That is not a flaw in the math. That is the math telling you that the concept of a photon at rest is meaningless. Photons do not sit still. They move at the speed of light, always, in every reference frame. That is the only mode of existence available to them. From a photon's point of view, If it had one, the universe is contracted to zero thickness in the direction of motion. Length contraction, the partner to time dilation, also goes to infinity at light speed. An object moving at 99% of light speed is length contracted by a factor of about 7. A meter stick moving past you looks about 14 centimeters long in the direction of motion. At 99.9%, it looks about 4.5 centimeters long. At light speed, it contracts to zero. The entire universe, stretched out in front of a photon, is compressed into a plane with no thickness. From the photon's perspective, there is no distance to travel because distance itself has collapsed. Departure and arrival are the same point. The photon does not cross space. Space does not exist for it in the direction it is moving. It is emitted and absorbed in the same instant at the same location, even though, from our perspective, it traveled 1 billion light-years over 1 billion years. This is what it means to move at the speed of light. You do not just move fast. You exit time. You collapse space. You stop being a thing that experiences duration and become a thing that exists timelessly, stretched across the universe in a single frozen moment. And if you have mass, you cannot get there. The universe forbids it, not because of some arbitrary rule, because the energy cost becomes infinite and the concept stops making sense. Now consider what happens if you try to go faster than light, not just approach it. Exceed it. Move at twice the speed of light, 3 times, 10 times. What do the equations say? They say nonsense. The Lorentz factor, which is 1 divided by the square root of 1 minus velocity squared divided by c squared, becomes imaginary, literally. The term under the square root goes negative. The square root of a negative number is an imaginary number, a mathematical construct that involves the square root of -1. Imaginary numbers are useful in physics. They show up in quantum mechanics. They show up in electrical engineering. But when a Lorentz factor turns imaginary, it means you have left the realm of physical possibility. The equations are not describing something real. They are describing something that does not exist in spacetime as we understand it. What would an imaginary Lorentz factor even mean? It would mean time is not just stopped, it is rotated into a different axis entirely. It would mean space and time have swapped roles. It would mean causality, the principle that cause precedes effect, has broken down. And once causality breaks, the universe stops making sense. Events no longer happen in order. Effects can precede their causes. You can receive a message before it was sent. You can arrive at a destination before you left. Faster than light travel is not just technologically difficult, it is conceptually incoherent. It is not a matter of building a better engine or finding more energy. It is a matter of asking the universe to do something it is not structured to allow. Here is why. Special relativity tells us that simultaneity is relative. 2 events that happen at the same time in one reference frame do not happen at the same time in another reference frame, moving relative to the first. If you are moving fast enough, events that are in my future can be in your past. That is fine, as long as no information travels faster than light. The relativity of simultaneity does not create paradoxes because signals are limited to light speed, and that limitation protects causality. But if you could send a signal faster than light, you could use the relativity of simultaneity to send that signal into your own past. You could create a causal loop. You could send a message that arrives before it was sent. You could, in principle, prevent yourself from sending the message in the first place. That is not just strange, that is logically impossible. The classic thought experiment involves 2 observers moving relative to each other at high speed. Observer A sends a faster-than-light message to observer B. from observer B's reference frame, the message arrives at a certain time. Observer B immediately sends a faster-than-light reply back to observer A. But because of the relativity of simultaneity from observer A's reference frame, the reply arrives before the original message was sent. Observer A receives an answer before asking the question. That is a closed time-like curve, a loop in time, and closed time-like curves are a problem. They allow for time travel paradoxes. You could go back and prevent your own birth. You could kill your grandfather before your father was born. The universe would have to resolve contradictions that have no resolution. Most physicists believe the universe does not allow this, not because of some moral objection to time travel, because the math breaks down and the structure of spacetime does not support it. Stephen Hawking proposed what he called the chronology protection conjecture. The idea is that the laws of physics, whatever they turn out to be at the deepest level, conspire to prevent closed time-like curves. Whenever you try to build a time machine, something goes wrong. The energy requirements become infinite. Quantum fluctuations destroy the structure. The universe throws up a barrier. The conjecture is not proven. It is a hypothesis. But the fact that we do not observe time travel paradoxes, the fact that causality seems to hold everywhere we look, suggests that something is protecting the timeline, and the speed of light is the first line of defense. If nothing can travel faster than light, then no signal can loop back on itself. Causality is safe. Time flows forward. Cause precedes effect. The universe makes sense. The speed of light is not just a speed. It is the speed of causality. It is the rate at which cause can propagate to effect. When you push a domino and it falls, the next domino does not fall instantly. The force propagates through the material of the first domino at the speed of sound in that material. When you flip a light switch and a bulb turns on, the signal does not travel instantly. It propagates through the wiring at a significant fraction of the speed of light, depending on the properties of the wire. When the sun explodes, if it ever does, Earth will not feel the change in gravity for 8 minutes, the time it takes for the gravitational wave to cross the distance between the sun and Earth. Every interaction, every force, every change propagates at a finite speed. And the maximum speed, the speed that cannot be exceeded, is the speed of light. That is the speed limit on causality. It is the speed at which now becomes the future. And you cannot outrun it, because outrunning it would mean escaping causality, and escaping causality means ceasing to be part of the physical universe. Faster-than-light travel is sometimes portrayed in fiction as a matter of going really fast or finding a shortcut through space, warp drives, wormholes, hyperspace. Some of those ideas are explored in general relativity, and some of them might, hypothetically, under conditions that probably do not exist, allow you to travel between 2 points faster than light would take to travel the normal route. But those are not examples of moving faster than light locally. They are examples of bending spacetime so severely that the distance shrinks. A wormhole, if one could exist, is a tunnel through spacetime. You do not move faster than light through the tunnel. You move slower. But the tunnel is shorter than the normal path through space, so you arrive sooner. That does not violate causality because you are not moving faster than light relative to the space you are moving through. You are taking a shortcut. The shortcut might be impossible to create. It might require exotic matter with negative energy density, which has never been observed and probably does not exist. But conceptually, it does not break causality the way moving faster than light locally would. Moving faster than light locally means moving faster than c through normal spacetime. That is what the equations say is impossible. And the reason is not that we lack the technology. The reason is that the structure of spacetime does not support it. Time and space are interwoven. The faster you move through space, the slower you move through time. At exactly the speed of light, you stop moving through time altogether. There is no speed faster than that which still involves time. Going faster than light does not mean going faster. It means transforming into something that does not experience time, does not traverse space in the normal sense, and does not interact causally with the rest of the universe. It means becoming something other than a physical object. That is not a limitation of engineering. That is a statement about what it means to exist. Photons exist in that other mode. They are massless. They move at the speed of light. They do not experience time. They do not have a rest frame. From their perspective, emission and absorption are simultaneous. They exist timelessly, stretched across space, connecting events that are causally linked but separated by distance. They are the messengers, the carriers of information, the threads that stitch the universe together, and they move at c because that is the only speed available to them. They cannot slow down, they cannot stop. They are born moving and they die moving, and in between, from their perspective, nothing happens. Zero time elapses. The journey is instantaneous. The destination is the origin. The universe collapses into a single point. For everything else, for every particle with mass, for every object made of matter, the speed of light is a wall. Not a physical wall you can touch, a mathematical wall embedded in the structure of spacetime. Approach it and time slows down. Energy requirements grow without bound. The closer you get, the harder it becomes to go faster. You can get arbitrarily close, as the Large Hadron Collider demonstrates. 99.99991%. But that last gap, that final sliver, is infinite. It does not matter how much energy you add, you will never close it. The universe is not being stubborn. The universe is following the rules, and the rules say that massive particles do not reach light speed. They approach it asymptotically. They get closer and closer, but they never arrive. And at exactly light speed, the equations break. Time stops. Distance vanishes. Causality ends. You stop being a thing that experiences the universe and become a thing the universe uses to connect its events. This is the ultimate consequence of the speed of light being absolute. It is not just that nothing can go faster. It is that reaching the speed of light means exiting the normal flow of time. It means collapsing space to zero thickness. It means existing in a state where past and future are the same moment. Photons live there. You do not. You are made of particles with mass. You experience time. You traverse space. You exist in a reference frame where cause precedes effect and where the universe unfolds one moment at a time. And the reason you exist that way, the reason time flows for you and space has extension and causality holds, is because you are not moving at the speed of light. You are moving slower, slow enough that time still exists for you, slow enough that the universe has not collapsed into a single instant. The speed of light is the dividing line. On one side, time exists, motion has meaning, cause and effect are sequential. On the other side, time stops, space collapses, causality becomes undefined. That line is not arbitrary. It is built into the fabric of spacetime. It is enforced by the equations of relativity, confirmed by every experiment ever conducted and embedded in the structure of quantum field theory. The speed of light is the edge of time. Cross it, and you stop being part of the story. You become part of the structure. A thread woven into the tapestry, a photon, a messenger, a timeless connection between events that, from the perspective of everything else, are separated by vast distances and vast durations. But from the photon's perspective, they are the same event, the same moment, the same point. And that is why faster-than-light travel is not just impossible, it is meaningless. It is asking to move faster than timelessness, faster than the rate at which the universe connects cause to effect, faster than the speed at which now becomes next. There is no faster, there is only c. The speed of light is not the speed at which light happens to move, it is the speed at which the universe operates. It is the clock speed of reality, the rate at which causality propagates, the boundary between things that experience time and things that do not. And everything in the universe, every particle, every force, every interaction respects that boundary, not because it has to, because that is what it means to be part of the universe. That is what it means to exist in space-time. That is the rule, and the rule is not negotiable. The universe does not bend on this. The speed of light is absolute. Time stops at c, and beyond c there is nothing. Just the edge of what is possible, and the beginning of what is not. Everything in the universe, every particle, every force, every interaction respects that boundary, not because it has to, because that is what it means to be part of the universe. That is what it means to exist in space-time. That is the rule, and the rule is not negotiable. But calling C a rule makes it sound like something imposed from outside, like a law passed by some cosmic legislature. That is the wrong picture. The speed of light is not a restriction. It is a definition. It is the heartbeat of the universe, the tempo at which reality unfolds. Every process that happens, every interaction that occurs, every signal that propagates, every cause that leads to an effect, does so at a rate that is ultimately governed by this one number: 299,792,458 meters per second. That is not a speed limit. That is the speed of existence itself. Think about what that number actually represents. It appears in Einstein's equations. It appears in Maxwell's equations. It shows up in quantum field theory. It shows up in thermodynamics. It connects energy to mass. It connects electric fields to magnetic fields. It sets the rate at which gravitational waves ripple through space-time. It determines how fast information can spread from one point to another. Every fundamental equation that describes how the universe works has C sitting in it somewhere, not as a variable but as a constant, a fixed number that does not change based on where you are, when you are, or how fast you are moving. It is the same in every reference frame, the same at every point in space, the same at every moment in time. The universe runs on C the way a clock runs on a spring. Remove it and nothing works. Everything stops. In 1983, the international scientific community did something remarkable. They stopped trying to measure the speed of light, not because they gave up, because they had measured it so precisely that further refinement was pointless. The measurements had converged. Multiple independent experiments using different methods had all arrived at the same answer to within a tiny margin of error. So the community made a decision. They defined the meter, the fundamental unit of distance, as the length light travels in 1,299,792,458th of a second. That locked C in place. It is no longer a measured quantity. It is a defined constant, exactly 299,792,458 meters per second by definition. The meter is now defined in terms of C, not the other way around. That is how fundamental the speed of light is. It is the reference point, the anchor, the thing we use to define everything else. That decision was not arbitrary. It was recognition that C is more fundamental than distance. Distance is something we measure. C is something the universe uses to connect space and time. Defining the meter in terms of c means we are using the structure of spacetime itself as our ruler. We are not measuring the universe against some external standard. We are using the universe's own internal structure as the standard. That is a subtle but profound shift. It means c is not a property of light, it is a property of spacetime. Light just happens to move at that speed because photons are massless and massless particles move at c. But c would still exist even if photons did not. It is the conversion factor between space and time. The rate at which 1 second of time corresponds to 299,792,458 meters of space. It is built into the fabric of reality. Here is another way to think about it. Imagine you are standing on Earth and you look up at the sun. The light you see left the sun 8 minutes and 20 seconds ago. You are not seeing the sun as it is now. You are seeing the sun as it was 8 minutes and 20 seconds in the past. That delay is not a transmission time in the usual sense. It is the gap between cause and effect. The sun emits a photon. 8 minutes and 20 seconds later, that photon hits your eye. The emission is the cause, the absorption is the effect, and the maximum rate at which the cause can lead to the effect is c. If the sun exploded right now, you would not know it for another 8 minutes and 20 seconds. The explosion would happen, the light would start traveling toward Earth, and for 8 minutes and 20 seconds, you would still be seeing the old sun, the one that existed before it exploded. The information that the sun is gone would propagate toward you at the speed of light, and you would not receive that information until it arrived. Causality is limited by c. Causes cannot instantly produce effects across distance. They have to wait for the signal to propagate, and the signal propagates at c. This is true for everything, not just light. Gravity propagates at the speed of light. If the sun disappeared, Earth would continue orbiting the now absent sun for 8 minutes and 20 seconds before the change in the gravitational field reached us. Then, suddenly, Earth would stop feeling the sun's gravity and would start moving in a straight line, flying off into space. The gravitational influence does not act instantaneously. It propagates as a wave, a ripple in the curvature of spacetime, and that ripple moves at c. Electromagnetic forces propagate at c. The strong nuclear force, mediated by gluons, propagates at c because gluons are massless. The weak nuclear force propagates slower than c because the W and Z bosons that carry it have mass, but the upper limit is still c. No force, no interaction, no influence propagates faster. The speed of light is the maximum rate at which anything can affect anything else. It is the speed of causality that has profound implications for the structure of spacetime. Every event in the universe has a light cone. Picture a point in spacetime, a specific location at a specific moment. From that point, imagine light spreading outward in all directions at the speed of light. As time passes, the light forms an expanding sphere. In spacetime, that sphere is not a sphere, it is a cone. The tip of the cone is the original event. The surface of the cone represents all the points in spacetime that light from the original event can reach as time goes forward. Inside the cone is the future light cone, the region of spacetime that can be influenced by the original event. Outside the cone is the region that cannot be influenced by the original event, at least not yet. The event at the tip of the cone can send a signal, a photon, a gravitational wave, anything moving at or slower than c, and that signal will eventually reach every point inside the future light cone. But it will never reach any point outside the cone unless that point moves into the cone later. The cone expands as time goes forward, sweeping up more and more of spacetime, but at any given moment there are points that are outside the cone. Those points are causally disconnected from the original event. Nothing the original event does can affect them, not yet. The same applies in reverse. Every event has a past light cone, the set of all points in spacetime from which a signal could have reached the event. If something happened outside your past light cone, it cannot have affected you. The signal from that event has not had time to reach you yet. It is still traveling through space at the speed of light, and until it arrives, the event might as well not have happened as far as you are concerned. Your present moment, the now you are experiencing right this second, is determined entirely by events inside your past light cone. Everything else is either too far away or too recent to have reached you. The light cones define your causal structure. They divide the universe into three regions: the past, the events that could have influenced you; the future, the events you could influence; and elsewhere, the events that are causally disconnected from you right now. Elsewhere is not in your past and not in your future. It is outside your light cone. It exists, but it has not interacted with you yet. The boundaries of those regions are set by C. Change C, and the light cones change shape. Make C infinite, and the cones disappear. Everything would be in everyone's past and future simultaneously. Causality would collapse. Time would lose meaning. The fact that C is finite is the reason time exists as a meaningful concept. It is the reason the universe has a history, a present, and a future that are distinct from each other. Now scale that up to the entire universe. The universe is about 13.8 billion years old. That means light has had 13.8 billion years to travel. The farthest distance light could have traveled in that time is about 13.8 billion light years, which works out to roughly 426 billion trillion kilometers. That distance defines the observable universe. It is not the entire universe. It is the part of the universe we could possibly see because light from those regions has had time to reach us. Anything farther away than that is outside our cosmic light cone. The light from those regions has not reached us yet. It is still on its way, and because the universe is expanding, some of it never will. There are galaxies out there whose light left them billions of years ago and is heading in our direction right now. But because space itself is expanding, the light is losing ground. It is moving toward us at the speed of light, but the space between us and it is stretching faster than the light can cross it. The gap is growing. The light will never arrive. Those galaxies are permanently outside our observable universe. We will never see them. Not because our telescopes are not good enough, because the speed of light is finite and the expansion of space is too fast. This is one of the strangest consequences of C being finite. There are parts of the universe we can never observe. Not someday, not with better technology, never. The information is out there. Galaxies are shining, stars are exploding, black holes are colliding. But the signals from those events will never reach us because the expansion of space has carried them beyond the cosmic horizon, the boundary of the observable universe. That boundary is set by C. If C were infinite, there would be no horizon. We could see everything, everywhere, all at once. But C is finite, so we cannot. We are limited to observing the region of space whose light has had time to reach us. And that region is growing, but not fast enough to catch up with the expansion. The observable universe is getting bigger, but the actual universe is getting bigger faster. We are falling behind. The horizon is receding. And there is nothing we can do about it because we cannot send signals faster than C, and neither can the universe. The expansion of the universe is one of the few things that can move faster than C without violating relativity. That sounds like a contradiction, but it is not. The expansion is not motion through space. It is the expansion of space itself. Galaxies are not flying through space away from us. Space is stretching, carrying the galaxies with it. The galaxies themselves are not moving faster than c relative to the space they are in. But the space between us and them is growing so fast that the distance is increasing faster than light could cross it. That is allowed. General relativity, Einstein's theory of gravity, does not prohibit space from expanding faster than c. It only prohibits objects from moving through space faster than c. The distinction matters. An object moving through space has to obey the rules of special relativity. Space itself does not. Space can do whatever it wants, and what it is doing is expanding, and in some regions it is expanding fast enough that light cannot keep up. Those regions are lost to us. We will never see them. They are beyond the horizon, and the horizon is set by c. Closer to home, c determines something much simpler but no less profound. It determines what we mean by now. Common sense says that now is the same for everyone. Right now, as you are reading this, something is happening on the other side of the planet. Something is happening on Mars. Something is happening in the Andromeda galaxy, and all of those things are happening now, simultaneously, at the same time. But relativity says that is wrong. Simultaneity is not absolute. It depends on your reference frame. Two events that happen at the same time in one frame do not happen at the same time in another frame, moving relative to the first. What you call now is different from what someone moving relative to you calls now, and the difference is determined by c. If you could instantly send a signal to someone on the other side of the galaxy, you could synchronize your clocks and agree on what now means. But you cannot send an instant signal. Signals travel at c or slower. By the time your signal reaches the other person, time has passed. They can send a signal back, but by the time it reaches you, more time has passed. You can never agree on a single moment that is now for both of you, unless you are in the same location. Simultaneity is local. It breaks down over distance, and the reason it breaks down is that c is finite. If c were infinite, signals would propagate instantly, and simultaneity would be absolute. Everyone would agree on what now means, but c is finite, so they do not. Now is relative. It depends on your motion. It depends on your location. It depends on your light cone, and the light cone is set by c. This is not just a quirk of relativity. It is a fundamental feature of how the universe is structured. Space and time are not separate. They are woven together into space-time, and the speed of light is the thread that does the weaving. You cannot talk about time without talking about space. You cannot talk about simultaneity without talking about light cones. You cannot talk about causality without talking about c. They are all connected. The speed of light is the thing that connects them. It is the rate at which space converts into time and time converts into space. It is the exchange rate between the two. And because that exchange rate is fixed, the structure of spacetime is fixed. Change c, and you change the structure of reality itself. There is a deeper beauty here. The speed of light unifies physics in a way nothing else does. Energy equals mass times the speed of light squared. That equation is not just a formula for nuclear reactions. It is a statement that mass and energy are the same thing. Mass is frozen energy. Energy is liberated mass. The conversion factor between them is c squared. That squared term is what makes the conversion so powerful. A tiny amount of mass corresponds to an enormous amount of energy. The sun converts 4 million tons of mass into energy every second. 4 million tons. That energy is what makes the sun shine. It is what makes life on Earth possible. And the equation that describes the conversion has c sitting in the middle of it, squared. turning a small mass into a staggering energy. Maxwell's equations, the equations that describe electricity and magnetism, predict that electromagnetic waves propagate at a speed equal to 1 divided by the square root of the permittivity and permeability of free space. Plug in the measured values of those constants, and you get 299,792,458 meters per second. Maxwell did that calculation in the 1860s and realized he had just calculated the speed of light. That was the moment physicists understood that light is an electromagnetic wave, not a separate phenomenon, not something different. Light is electricity and magnetism oscillating together, propagating through space at c. The speed of light is built into the equations of electromagnetism. It emerges naturally from the theory. It is not added in as a free parameter. It is derived. It is a consequence of how electric and magnetic fields interact, and the fact that it matches the observed speed of light was one of the great unifications in physics. Optics and electromagnetism turned out to be the same subject. Quantum electrodynamics takes this further. The coupling between electrons and photons, the strength of the electromagnetic interaction, is set by a dimensionless number called the fine structure constant. That constant is about 1 divided by 137. Nobody knows why it has that value. It is one of the great mysteries of physics. But whatever the reason, that number determines how strongly charged particles interact with light, and buried in the definition of that constant is c. The speed of light appears in the formula for the fine structure constant. Change c, and you change the strength of electromagnetism. You change the size of atoms. You change the energy levels of electrons. You change chemistry. You change biology. You change everything. The speed of light is not just a speed, it is a structural constant that determines how the electromagnetic force operates. And since the electromagnetic force is what holds atoms together, what makes molecules bond, what allows chemistry to happen, the speed of light is ultimately responsible for the fact that matter has the properties it does. Change c, and you do not just change how fast light moves, you change what matter is. Experiments over the past several decades have tested whether c actually is constant. Maybe it was different in the early universe. Maybe it changes over time. Maybe it varies with the wavelength of light or the energy of the photon. High-energy astrophysics experiments have looked for variations in c by observing photons from distant gamma-ray bursts and quasars. If the speed of light depended on energy, high-energy photons would travel at a slightly different speed than low-energy photons. Over a journey of billions of light-years, that difference would add up. The photons would arrive at different times. Detectors on Earth would see a delay. They do not. Observations from experiments like LHASO, which studies high-energy gamma rays from cosmic sources, have found no variation in the speed of light across photon energies spanning many orders of magnitude. Photons with energies of 1 giga-electron-volt and photons with energies of 1 tera-electron-volt, a factor of 1,000 different in energy, all travel at the same speed. The measurements are precise enough that if there were a variation of even 1 part in 100,000 billion, it would show up. It does not. The speed of light is constant across energy scales, across cosmic distances, across redshifts up to z equals 2, meaning light that has been traveling for more than 10 billion years. C does not change. It is the same now as it was when the universe was a quarter of its current age. It is the same here as it is in a galaxy 10 billion light-years away. It is the same for low-energy photons as it is for high-energy photons. C is a true constant, not approximately constant. Not constant within measurement error, constant. That constancy is what makes physics possible. If c changed from place to place or time to time, the laws of physics would change too. Chemistry would be different in different regions of space. Stars would burn differently at different times in cosmic history. The cosmic microwave background, the afterglow of the Big Bang, would have a different temperature. Galaxies would evolve differently. None of that is observed. Everything we see is consistent with c being the same everywhere and every when. The universe runs on a fixed constant, and that constant is not negotiable. It is not adjustable. It is the heartbeat, the tempo, the rate at which the universe unfolds. And it has been the same tempo for the entire history of the cosmos, from the first microseconds after the Big Bang to today, 13.8 billion years later. The beat has not changed. The rhythm is constant. The universe is ticking along at c, and it has been ticking at c since the beginning. That is the real meaning of the speed of light. It is not a barrier you run into when you go too fast. It is the clock speed of causality, the rate at which the universe processes the transition from one moment to the next, the maximum rate at which information can flow from one point to another, the boundary of the light cone that defines what can affect what, the conversion factor between space and time, the unifying constant that connects energy and mass, electricity and magnetism, quantum mechanics and relativity. The speed of light is the pulse of the cosmos, the rhythm underneath everything. The rule that enforces causality, protects the arrow of time, and prevents the universe from collapsing into a timeless, causally incoherent mess. It is not a limitation, it is the foundation. Without c, there is no structure. Without c, there is no time. Without c, there is no universe. And the universe, as far as we can tell, has no intention of changing that. The speed of light is what it is, and it has been what it is for as long as there has been a universe to measure it in. The cosmos is not slowing down or speeding up. It is running at the same rate it has always run, and that rate is c. 299,792,458 meters per second, the heartbeat of reality. Steady, unchanging, absolute. That is the speed at which the universe exists, and once you see it that way, once you stop thinking of the speed of light as a speed and start thinking of it as the fundamental rate at which reality happens, the question changes. The question is not, why can nothing go faster than light? The question is, what does it mean to live in a universe that operates at this speed, and what does that reveal about the nature of existence itself? Because the speed of light is not just a fact about photons, it is a fact about time, space, causality, and the structure of everything that exists. It is the thread that holds the universe together. And if you pull on that thread, if you really look at what it means, you start to see that the universe is not a collection of separate things happening in separate places at separate times. It is a single unified process unfolding at a single constant rate, and that rate is c, always has been, always will be. There is a deeper reframing here that most people miss. We talk about the speed of light as a barrier, a limit, a wall you cannot cross. That framing is backwards. The speed of light is not restricting anything. It is not holding you back. It is not a cosmic guardrail preventing you from going too fast. The speed of light is the rate at which the universe writes itself into being. It is the maximum speed at which reality can process the transition from one moment to the next. It is not a limitation. It is the definition of change itself. Think about what that means. Every event that happens, every interaction, every particle collision, every photon emitted, every force transmitted, happens because information is moving from one point in spacetime to another. Cause propagates to effect. A photon leaves the sun. 8 minutes later, it arrives at Earth. That delay is not a transmission time. It is the gap between one state of the universe and the next. The photon leaving is one event. The photon arriving is another event. And the universe cannot update from the first event to the second event faster than c allows. That is not because the photon is slow. It is because c is the rate at which the universe computes, the rate at which now becomes the next moment, the rate at which reality unfolds. Imagine the universe as a vast calculation. Every particle, every field, every interaction is a term in that calculation. The universe is solving the equations of physics in real time, moment by moment, updating every point in space based on the information arriving from nearby points. That updating happens at a finite rate. Information cannot propagate infinitely fast because the universe cannot process infinitely fast. There is a maximum speed at which the update can occur, and that speed is c. It is not that photons happen to move at that speed. It is that c is the speed at which the universe itself operates. Photons move at c because there is nothing slowing them down. They are riding the wave of the universe's own internal clock. They are moving at the rate reality happens. This is a profound shift in perspective. We tend to think of the universe as a stage, a static background where events occur. Space and time are the stage. Particles and forces are the actors. The actors move around on the stage, interacting with each other, and the stage just sits there, passive, unchanging. But that picture is wrong. The stage is not passive. The stage is dynamic. Space and time are not a backdrop. They are part of the process. They are part of the calculation, and the rate at which that calculation runs is c. Every point in space is connected to every other point by the speed of light. If something happens here, the information about that event spreads outward at c. It reaches nearby points first, then more distant points, then even more distant points, at a rate determined by c. The universe does not know instantly that something happened. It finds out gradually at the speed of light as the information propagates outward. That propagation is not light traveling through space. That propagation is the universe updating its state. The universe is rewriting itself, point by point, moment by moment, and the rate at which it rewrites itself is c. This is why causality works. Cause precedes effect because information takes time to travel. The cause happens. The information propagates at c. The effect happens when the information arrives. There is a delay, and that delay is what gives time its structure. Without that delay, without the finite speed of information, there would be no distinction between past and future. Everything would happen at once. The universe would be a timeless block where all events are simultaneous. But the universe is not like that. It has a past and a future. It has a direction. It has an arrow of time. And that arrow exists because c is finite, because the universe takes time to update, because reality unfolds at a specific rate, and that rate is the speed of light. This is the ultimate answer to the question of why nothing can go faster than light. It is not that the universe is enforcing a rule. It is that going faster than light would mean going faster than the rate at which the universe itself operates. It would mean processing information faster than reality can process it. It would mean updating your state before the universe has had time to calculate what your state should be. That is not possible. Not because of some external constraint, because it is internally contradictory. The universe is the calculation. You cannot outrun the calculation. You are part of it. Going faster than light would mean existing outside the flow of reality, and there is no outside. There is only the flow, and the flow runs at c. Some physicists have speculated that c might not be a truly fundamental constant. Maybe it is an emergent property. Maybe it arises from deeper structures we do not yet understand. There are theories that describe the vacuum of space as having properties similar to a material medium, with an effective elasticity and density. In those theories, the speed of light is analogous to the speed of sound in a solid. Sound travels through a material at a speed determined by the stiffness and density of that material. The stiffer and less dense the material, the faster sound travels. If space-time itself has similar properties, then c might be the speed at which disturbances propagate through the fabric of space, determined by the vacuum's stiffness and density. Change those properties and you change c. That is an interesting idea, but it does not change the fundamental point. Even if c is emergent, even if it arises from some deeper layer of physics we have not discovered yet, it is still the rate at which reality operates. Whatever mechanism produces c, the result is the same. Information propagates at c. Causality is limited by c. Time and space are connected by c. The universe unfolds at c. Whether c is a fundamental constant written into the laws of physics at the deepest level, or an emergent property arising from the structure of space-time, does not matter for most purposes. The universe behaves as if c is absolute. Every measurement ever made confirms that c is the same everywhere, at all times, for all observers. If it is emergent, it is remarkably stable. Stable enough that it might as well be fundamental, and stable enough that we can treat it as the heartbeat of the cosmos without worrying about whether there is an even deeper heartbeat underneath. There is an elegance to all of this that is easy to miss. The speed of light is not just one constant among many. It is the constant that ties everything else together. Energy and mass are related by c². Space and time are related by c. Electric fields and magnetic fields are related by c. The equations of electromagnetism predict c. The equations of quantum field theory predict c. The equations of general relativity treat c as the fundamental conversion factor between the geometry of spacetime and the dynamics of matter and energy. Every major theory in modern physics has c sitting at its core, not as an input but as an output, not as something you put in by hand, but as something that falls out naturally when you write down the equations. That is a sign that c is not arbitrary. It is not a random number that happened to be what it is by accident. It is a structural feature of the universe. It is part of the design, if design is the right word. Part of the architecture, part of the logic. And that logic is airtight. If you want a universe where causality works, where time has a direction, where information can propagate but not infinitely fast, where space and time are unified into a single structure, you need a constant like c. You need a maximum speed at which influences can travel. Set that speed to infinity and causality collapses. Set it to a finite value, and you get the universe we live in. A universe where the past is fixed, the future is open, and the present is the boundary between them. A universe where events are ordered, where cause precedes effect, where time flows forward, where things happen in sequence rather than all at once. That is the universe we observe. And the thing that makes it work, the thing that enforces the structure, is c. There is something almost musical about it. The universe has a tempo, a beat, a rhythm that never changes. Every process, every interaction, every propagation of force or information happens in time with that beat. Photons move at the beat, gravitational waves move at the beat, the electromagnetic field updates at the beat. Particles with mass move slower than the beat, but the beat sets the limit. Nothing outruns it. Nothing even reaches it unless it has no mass. The beat is steady, unvarying, absolute, and it has been the same beat since the first moment of the Big Bang, 14 billion years ago. The universe came into existence ticking at c, and it has been ticking at c ever since. The tempo has not changed, the rhythm is eternal. That constancy is one of the most remarkable features of the cosmos. In a universe that is expanding, cooling, evolving, where galaxies form and stars die and black holes evaporate, where entropy increases and structure dissolves, the speed of light does not change. It is the same today as it was a billion years ago. It is the same here as it is in a galaxy 10 billion light-years away. Experiments searching for variations in c have found nothing. High-energy photons and low-energy photons travel at the same speed. Photons from distant quasars that have been traveling for most of the age of the universe arrive at the same time, regardless of their energy. If c varied with energy, even by a tiny amount, the photons would arrive at different times. They do not. If c varied with time, the cosmic microwave background would look different. It does not. If c varied with location, the laws of physics would be different in different parts of the universe. They are not. Everything we see, everywhere we look, at every scale, at every time, is consistent with c being exactly the same. The universe runs on a fixed clock, and that clock ticks at 299,792,458 meters per second. No faster, no slower, always. That raises a philosophical question. Why this value? Why 299,792,458 meters per second and not some other number? The honest answer is we do not know. There is no deeper theory that predicts that specific value. It is a measured constant. We can define the meter in terms of it, which locks the number in place by definition, but that just moves the question. Why does light travel the distance we call a meter in the time we call 1,299,792,458th of a second? Why that ratio? Why not twice as fast? Why not half as fast? What sets the clock speed of the universe? Nobody knows. It is one of the deepest mysteries in physics. The speed of light is a fundamental constant, but unlike some other fundamental constants, it has units. It is measured in meters per second. That means it depends on how we define meters and seconds. But if you convert it into natural units, units where c equals 1, then the question becomes why the universe has the structure it does. Why is spacetime configured such that the conversion factor between space and time is what it is? Why does the vacuum have the properties it does? Why do massless particles propagate at the rate they propagate? These are questions we can ask, but we do not have answers, not yet. Maybe someday a deeper theory will explain why c has the value it has. Maybe there is some underlying principle that fixes it. Or maybe it is arbitrary. Maybe it could have been different in a different universe, and the value we observe is just the value that happens to exist in this universe. We do not know. What we do know is that the value we have is the value that makes the universe work. Change c, and you change everything. Make c larger, and causality operates faster. Events that are far apart in space can influence each other more quickly. The light cones expand. The universe becomes more connected. Make c smaller, and causality operates slower. Events take longer to influence each other. The light cones shrink. The universe becomes more fragmented. Make c infinite, and causality becomes instantaneous. Everything affects everything instantly. Time loses its structure. The past and future collapse into a single moment. Make c zero, and nothing can propagate. Every point in space is isolated. No forces, no interactions, no change. The universe freezes. The value of c, whatever that value is, determines the pace at which the universe operates. And the pace we have, the pace that exists, is the pace that allows for complexity, structure, causality, time, change, and existence as we understand it. That is what it means to say that c is the rate at which reality unfolds. It is not a restriction, it is the definition. It is the speed at which the universe writes the next moment into being. It is the speed at which information flows from cause to effect. It is the speed at which fields update, particles interact, and forces propagate. It is the speed at which time becomes space, and space becomes time. It is the speed at which the cosmos computes the answer to the question, what happens next? And the answer to that question, the next frame of reality, arrives at a rate of 299,792,458 meters per second, every meter, every moment, without exception, without variation, without pause. You are living in that computation. Every thought you have, every breath you take, every heartbeat, every firing neuron, every molecular vibration is part of the process. Your existence is embedded in the flow of information propagating at c. The photons hitting your eyes right now left their sources fractions of a second ago. The electrical signals traveling through your nervous system move slower than c, limited by the properties of the cells carrying them, but the ultimate speed limit on those signals is still c. The electromagnetic forces holding your atoms together propagate at c. The gravitational force pulling you toward the Earth propagates at c. You are a pattern of information sustained by processes that operate at or below the speed of light. You cannot exist faster than c. Nothing can. Existence itself is bounded by c. It is the rate at which reality happens. It is the rate at which you happen, and that rate is not arbitrary. It is not a coincidence. It is the tempo of the universe, the clock speed of causality, the heartbeat of everything that is. The speed of light is not light's speed, it is reality's speed. It is the speed at which the cosmos unfolds, moment by moment, event by event, interaction by interaction. It is the speed at which now becomes next. It is the speed at which the universe writes itself into being. For thousands of years, humans looked up at the sky and wondered what light was, where it came from, how fast it moved. Galileo tried to measure it with lanterns on hilltops. Römer measured it by watching Jupiter's moons. Fizeau and Foucault measured it with spinning mirrors and toothed wheels. Einstein explained why it was constant. Feynman explained how it emerged from the quantum dance of photons and electrons. Particle physicists tested it by accelerating protons to within a hairbreadth of light speed and watching them refuse to go faster. Astronomers tested it by observing photons that traveled for billions of years and arrived at exactly the speed the equations predicted. Every measurement, every experiment, every test confirmed the same thing. The speed of light is 299,792,458 meters per second. Exactly, everywhere, always. And in 2025, with centuries of evidence behind us, with equations that predict reality to 12 decimal places, with machines that push particles to the edge of what is possible, we can finally say with confidence what the speed of light really is. It is not a barrier. It is not a limit. It is not a wall. It is the rate at which the universe operates. It is the maximum speed at which reality can process itself. It is the clock speed of existence. It is the tempo of causality. It is the heartbeat of the cosmos. It is the speed at which the universe unfolds. That is what Galileo was reaching for when he uncovered his lantern on a hilltop in 1638. He did not know what he was looking for. He did not have the tools to find it. but he asked the question, how fast does light move? And that question, pursued over centuries by countless minds working with ever more precise instruments, led to an answer far stranger and far more profound than anyone expected. Light moves at the speed it moves because that is the speed at which everything moves. Not through space, through time, through the unfolding of reality itself. Light moves at the speed of existence, and so does everything else. The universe is not waiting for us to catch up. It is not slowing down. It is not speeding up. It is ticking along at sea, the way it always has, the way it always will, writing each new moment into being at a rate of 299,792,458 meters per second. That is the speed of light. That is the speed of reality. That is the rate at which the universe exists. So here we are, 4 centuries after Galileo stood on a hill with a lantern, trying to catch something that moved too fast for human hands to measure. 3 centuries after Roma watched Jupiter's moons and realized light was not instant. A century after Einstein rewrote time itself to keep light's speed constant. Decades after Feynman showed us that light does not follow a single path but explores every path, that the universe is not choosing what happens but calculating it, summing over all possibilities, and the answer that survives is the one we call reality. And the answer, every time, is 299,792,458 meters per second. Not because the universe decided that number sounded nice, because that is the rate at which causality operates, the rate at which now becomes next. The rate at which the fabric of spacetime updates itself, moment by moment, interaction by interaction, weaving the present into the future at a tempo that has not changed since the first instant of the Big Bang. The speed of light is not light's property. It is the universe's clock speed, the maximum rate at which information can flow, the boundary between things that experience time and things that do not. Cross that line and time stops, space collapses, you stop being a participant in reality and become a thread woven into its structure. Photons live there, you do not. You are made of particles with mass, and mass means you are bound to time, bound to cause and effect, bound to the flow, and that flow runs at sea, always has, always will. The universe is not slowing down for you, it is not waiting, it is unfolding at the only speed it knows. The speed of existence itself, that is the limit, not a wall, a definition. And everything that happens, everything that ever has happened, or ever will happen, happens at that rate. The universe ticking forward, one moment at a time, at the speed of light.